Is Katie Glover here? Maybe not. Katie Glover has been, along with others, has been piloting our new remote certificate in climate adaptation, which will be available on a worldwide basis. We'll see how well we do, but I think we're ahead of the curve. As you also know, this is our 50th anniversary. And because of that, we can actually begin to talk about having a legacy. And this institute definitely has a legacy. We have had many very well-known people come through this institute. We've made major scientific advances. We've made major advances in innovation. We've worked on every single continent and covered more of those continents than probably anybody else altogether. We've worked in many oceans. We're multidisciplinary and interdisciplinary. In fact, we're the leaders in this university for interdisciplinary activities and research. We have, as you sum up all of the awards that have been gotten by the students, the staff, and the faculty, we have an unbelievably long list of awards. It would take me probably the first hour to list all of the awards that have been gotten by people in this institute. So this is a very special event for us, the Bourne Symposium. It's been going on for more than 30 years, and spoke to George. And I guess before this, there was a version of it, is that correct?
Yes, but I think specifically annual, 1992 or something that it changed.
So this is a big part of our legacy. And it's also the most important meeting of the year for us. It's a time when we get to hear primarily graduate students, but many of the faculty will be speaking too. And what you will hear here in the next 2 days are things that will become potentially major scientific achievement in the next 2 or 3 years. So keep your eyes and your ears open. And we look forward to hearing all of the wonderful presentations. Every single year, quite truthfully, they get better and better and better. So I'll turn it over to our first host, and we'll go from there.
Yeah.
Do we have enough chairs back there? Do we need any more chairs, or we're all set? Okay, we'll walk.
Okay. Oh, hello, I'm Emily Blackwood. I'm an interdisciplinary PhD student with a focus on archaeology. And today I'm going to be talking about some of the ethical aspects that I think we should be considering when utilizing virtual reality and 3D models in archaeological research. For my dissertation, I wanted to explore using VR as a platform to showcase archaeological data for the dual purposes of site analysis and public outreach. VR, in the simplest of terms, is a computer-generated simulated environment that uses data to create visualizations that can be both immersive and interactive. I think that this can be a really powerful tool if used appropriately. One of the sites that I'm simulating is located on the north central coast of Peru, as can be seen here in the left image. It's indicated by the upper red star. The outline of the ancient ocean can still be seen. The Andean Mountains sit to its east, and the Pacific Ocean is 5 kilometers to its west. In the upper right-hand corner is the HTC Vive, which is the VR headset that I'm using because it includes headphones for audio and handheld controllers for navigation around the space. The VR simulation that I'm working on can be seen here in the lower right-hand corner and was created using Unity 3D game engine. We have permission to excavate this site and publish our work. It's radiocarbon dated to approximately 6,500 calibrated years BP. It's the remains of a 9 by 8 meter granite stone structure, which is represented here, which is large for the time period. It's located at the top of an ancient sea cliff, and during occupation, the Pacific Ocean was right here at its edge. In present day, the ocean is 5 kilometers to the west, and as you just saw, When the ocean layer is turned off and back on, this makes a huge contextual and visual difference. The mollusk assemblage suggests warmer ocean temperatures during occupation than in present day. It's linked to a site that's 3 kilometers to the south, right here, through diagnostic artifacts. And it has the potential to be one of the oldest sites in the Americas with evidence of defensive measures. We would be like space. Yeah. It's supposed to like. No? No. Okay. Well, there's some slingstone piles that are supposed to appear here. And these extend from the structure and in front of it. So this is an excellent example of a site that could benefit from the creation of a simulated environment. It's extremely difficult, even having been there, to imagine what this area looks like and the environment experienced when the ocean was at its edge. We really need to like advance the slide.
It doesn't want to move, right?
Try the forward arrow. It's at the bottom right.
Oh, yeah. When you try clicking on, just click on the presentation maybe. And then,
oh, there it is.
Okay.
Yeah.
Right. Probably thought
next.
Yeah.
Those are the slingstone piles. There we go. Okay. So to further my simulation, I am currently using an app that uses LiDAR and photogrammetry to create 3D models that can be directly exported into Unity, which is the software that I'm using for the simulation, or shared as videos. But the fair warning, really read those licensing agreements closely, because a lot of these apps retain the right to use any models you've created for their own purposes without permission. And I just briefly wanted to mention LiDAR because it's a really incredible tool. You can create 3D models of entire sites. You need a phone that has LiDAR in it, so an iPhone 12 or newer, but photogrammetry works on any device. I used an iPhone 11 to make my models. These are 3 examples of modeled shells from the site in Peru. From left to right, they are a scallop, an oyster, and a clam. They're representative of warmer ocean temperatures, and they're not found in the region today. So these each had about 200 pictures. Again, this is done with photogrammetry, so you need to take images of the objects from all sides and all angles, and then the app processes it and removes all of the background noise, and you either end up with an accurate model or a failed one. And sometimes you can see where it failed, so you can add or remove pictures, reprocess it, and hope for a better result. A benefit of creating 3D models of shells is that if you can't identify the species, or you wanted to double check your identification, it can be sent via a link through the app or downloaded videos like these and be sent to a mollusk expert. A 3D model provides more information than photographs. They can also create better visualizations. They can be accurately measured within the app, and this really removes the frequency of handling artifacts. A downside is that it really drains your battery and it takes up a lot of space. So you're going to want a dedicated device. So archaeology has a tendency to focus on the cultural material itself rather than the people who created those records. We've normalized removing human agency from discussion and site narratives, and in doing so, don't often pause to think about the material we are making public or the harm that this can cause. So I really want to dive into some key concepts here that I think we should be thinking about when utilizing this kind of technology. I've just shown you a glimpse of what this can do, and I want to be really clear on this, is that just because something is available to use does not mean that we should be using it. A lot of harm has been done and is still being done in the name of science within this discipline. So these aren't meant to be short yes or no conversations. Trust needs to be built. And as archaeologists, we should accept the decision of the tribe or the community. If they say no, we should listen and respect that. So with the publication of cultural materials, it hasn't been standard practice to ask permission from the tribe or community on what to publish in site reports, photographs, presentation materials, etc. It's just done. This removes human agency and places all of the power with the archaeologist. There's a lot more to unpack here, and that's not to say that things shouldn't be published, but maybe just not publicly available outside the community without permission. Once published or publicly available data is out there, it's out there for all to see and use. There are countless instances of published photographs and artifacts and spaces that are considered sacred to communities and shouldn't be publicly seen, but they are. Intellectual property rights ties right into publication of cultural materials and who owns them. So who owns the 3D models and has the rights to them, the community or the creator. Is the 3D model then considered a separate entity from the original object? Accessibility, who has access to them? Are they in a shared repository where tribal or community members have access? Is there a privacy agreement? Are they behind a paywall? Are they publicly available? Commercialization ties in with all of the above. Who benefits or profits from this? Does it cause more harm than good? And looting. So looting refers to the stealing of artifacts from a site. This can be as simple as you're out on a hike and you see an artifact on the ground and you collect it and keep it for yourself, to intentional illegal digging at a site. Making data publicly available has a history of leading to looting, and this hurts everyone involved. An example is at the site in Peru. There's the presence of pearls, which can be seen here on the right. And we believe that while this was done in antiquity due to the site context, it still shows that once something that is considered valuable is known to the public, it's sought by the public. These pearls came from the backfill of a unit that had been disturbed. There we go. Sorry. Okay, so digital identity. The same type of records need to be kept when creating 3D scans and prints of artifacts as with the physical artifacts themselves. Otherwise, they lose their context and their narrative. The app that I use allows for captions where this information can be stored, but it should also be stored in a digital repository or printed and or written as a hard copy. Digital archives are only as sustainable as the server, the network, the cloud, whatever you're using. If it isn't upkept, it will be lost, and this can lead to mismanagement of cultural material. And also they can be hacked if they're not properly protected. And then there's the price tag of doing this. So it can be quite cost prohibitive. Quality 3D printers and filaments are not inexpensive. Quality scanners are not inexpensive. There's also the learning of new software and troubleshooting technology challenges and convincing collaborators of its worth. So for digital archaeology, we have reconnection with culture. So this is really important for tribal communities. Phones and tablets and computers can display the 3D objects that have been scanned and creates accessibility to artifacts that are housed or curated at universities, museums, and private collections. 3D prints can also allow for a form of physical connection without the risk of damaging the cultural material. We have a lot of oil on our hands. You can drop and break stone materials or ceramic materials, and oxidation also affects preservation. Sorry. Public outreach. This can refer to models of archaeological toolkits. So trowels, line levels, plumb bobs, things that people not in archaeology might not necessarily know what those are. Oftentimes when I describe what I do to people, they're like a garden trowel, you mean? And I'm like, no, not a garden trowel. So having a 3D model can be pretty beneficial. And also for teaching. In 2001, a law was passed in Maine that requires all Maine elementary and high schools to teach about Maine Indigenous peoples, and a lot of them still fall very short of this. I don't know if any of you going through the public school system, if you're from Maine, were taught anything about our Indigenous people, but I know I wasn't given a quality education, and by law we're required to. And from the literature review that I've done on looking up using digital artifacts and scanning within the discipline, the common denominator is that this technology is too new for organizations to develop discipline-wide guidelines. And I just think that's pretty ridiculous, because you can develop guidelines and amend them later, but if you don't have one set in place, there's no standard rule or like guide to show you what to do. It's really a free-for-all. And it's up to you to decide the ethics that you want to put in or not put in and how you want to use this. So just to summarize, 3D models and LiDAR have the potential to be impactful visual and analytical tools, but they should be used cautiously and respectfully. And I just wanted to thank the collaborative efforts of my committee members and the field team crew, the VEMU Lab, where I do a lot of this research, UMaine, and the Churchill Exploration Fund. Thank you. No idea where I am for time, so I don't know if there's time for questions. Does anyone have any questions?
We have 1 minute.
Okay, can also find me afterwards if we want to just keep on track.
So Emily, are you preparing a publication on this? Because it sounds like there's a need.
Oh, Dan. Dan. Yes, Elizabeth actually just mentioned that to me too. So yes, that's probably where that's headed.
Good.
Yeah, I think there's a pretty big need for that, and the fact that we don't have any guidelines because it's too new is.
I can think of several places you might put it, so let's talk about it.
Yeah. Thank you.
Hello, I'm Alexander Roman. I'm a current PhD student working with Aaron Putnam. My work is focused out in the Wind River Range in Wyoming at 44 degrees north, where I'm currently constructing a Burlington glacial chronology, which I am going to be using to test and assess the compatibility of several climatic mechanisms in the context of the last glacial maximum and its termination. What you're looking at is an image of a boulder line resting on a moraine crest in the Wind River Range, both of which were the result of a previous glacial advance and is our first hint into the glacial history of this area. So just to get us started, so we're all on the same footing, I'm going to quickly go over some context. So it is currently widely believed that a combination of orbital parameters, ice sheet feedbacks, and greenhouse gas forcing were the primary mechanisms and drivers of the most recent ice age climate and its termination. And this is evident by several recently published studies, such as Marcotte et al., who states that the last deglaciation was largely the result of a greenhouse gas dominated forcing, as well as Tierney et al. 2020, who suggests in addition to greenhouse gas forcing, the last glacial maximum climate was also the result of albedo feedbacks from that large terrestrial ice sheet. Now, originally, the orbital parameters and ice sheet feedbacks can be credited to Yugoslavian astronomer Milutin Milankovic, who thought that the insolation at 65 degrees north during the summer solstice controlled the waxing and waning of northern hemisphere ice sheets, which ultimately dictate the climate state of the globe. However, in 1984, glaciologist John H. Mercer discovered that southern hemisphere alpine glaciers both advanced and retreated almost synchronously with the northern hemisphere ice sheets in complete disregard of the opposing insolation signals that's experienced between the two hemispheres. He described this as defying all explanation and has since been coined by our group as Mercer's paradox. Other fallacies have been found as well. What you're looking at is a plot of the benthic 018 record in blue, which is thought to represent the global ice volume. And then in red is the insolation signal at 65 degrees north during summer solstice. As you can see, termination 1 and terminations 2 occurred during times of low insolation, while terminations 3 and 4 occurred during times of high insolation, kind of negating and almost disregarding the local insolation signal for when termination should or should not occur. As well, along with this, several studies have also found that southern hemisphere alpine glaciers retreated much more quickly and rapidly than can be solely explained by either orbital or greenhouse gas forcing. Now, this leads us to an interesting question. If not the Milankovitch hypothesis for an explanation for ice ages, then what? And it leaves a need to find a new mechanism that can explain and account for these synchronicities. And that is what brought me out to the Wind River Range, by this cute little red diamond there, as it would have been located on the periphery of the largest ice sheet on the world, the Laurentide ice sheet. And it's also located in the middle of a continent, which makes it a prime location for testing any ice sheet feedbacks, primarily albedo feedbacks would have had on the glaciers and therefore their climate. It's also located at a similar mid-latitude around 43, 44 degrees as the Southern Alps in New Zealand, which makes it a prime location to test and compare any effects and impacts the local insolation signal would have had on the glaciers. Now, the Wind River Range is located in the western part of Wyoming, and my field area, in particular Boulder Lake, is located on the west side of the range. It's one of the many lakes that now inhabit the numerous over-deepened valleys that line the perimeter of the Wind River Range. What you're looking at is a preliminary geomorphological map that I'm currently constructing of my field area. And I'll just quickly go over some of the symbology. So each one of these yellow dots represents a location where I have sampled a glacially deposited boulder. Everything in pink represents a moraine or a moraine ridge from the most recent glacial advance, the last glacial maximum. Everything in green out here represents moraines and moraine ridges from the penultimate glacial advance. This yellow is just representing active riverbeds, and this tannish color represents outwash plains, which are the result of glacial fluvial deposited material from outwash meltwater from the glacier. Now, the glacier would have advanced from the mouth of this valley and started forming all these features you see here before eventually retreating back up valley. Now, I've collected 130 samples over the past 2 field seasons, and I have received ages from a good handful of them. So I'm able to now start constructing a preliminary glacial chronology, which I'm fortunate enough to be able to share with you today. So I was able to date these outboard old moraines to what's known as the Bull Lake Advance. It's dated to around MIS 6. And although there are some obvious outliers, what I found interesting to note is that our methods are able to date rocks hundreds of thousands of years old at quite high precision. Moving towards the largest and most prominent feature, I have received ages between 21.2 and 36.4 thousand years, placing the construction of this feature as what's known as the Pinedale Advance, or that last glacial maximum, MIS 2, or even earlier. Between the spread of the ages and the geomorphology of this feature, featuring multiple interwoven crests and its just sheer size and dominance over the landscape, lead me to believe that this is indeed a composite feature that represents multiple advances of a glacier. And those advances include periods of around 21,000 years, 22, 23,000 years, and 26,000 years, potentially even 36, 37,000 years. Now, what's interesting about these 2 ages is that if they are indeed true, they represent and show that ice would have reached this maximum point several thousand years before the classical peak in global ice volume during the last glacial maximum. Oh, there we go. I also have several ages from glacial erratics, dating out to an average around 17,000 years, which represent and show that the glacier would have already started making its retreat back up valley and started terminating around that time. There we go. Now, when you look at my preliminary chronology in the context of the local insolation signal, it actually kind of makes sense in the context of the Milankovitch hypothesis, with the 2 largest moraine building events occurring in a trough in the signal, and the erratics represent that retreat of the glacier occurring during a time when the signal was rising. However, the story gets much more complicated when you begin to compare my chronology to those that have already been constructed in the Southern Alps. So what you're looking at here in black, blue, and green are three chronologies, three different areas in the Southern Alps that have been dated. And then down here in red is mine in Older Lake in the Northern Hemisphere. And what I want to first point out is that so each of these peaks represents a different moraine building event or a time when the glacier advanced and essentially reached equilibrium with its climate. And up here in orange is the local insolation signal for the Southern Hemisphere. Each one of these peaks seemingly occurs almost at random and complete disregard, some of them occurring during a time where it's falling, during a peak at high insolation, and other times when it's low. But secondly, and more importantly, is that each one of my peaks that represents a moraine building event has its corresponding peak in the Southern Hemisphere, including my 26,000 and 36,000 age boulders, which just boasts my confidence that they are indeed representing a past glacial extent and aren't outliers. This gets at the heart of what Mercer's paradox is. Why do glaciers in the Northern Hemisphere advance and retreat seemingly synchronously with those in the Southern Hemisphere if insulation is one of the main drivers or primary mechanisms of ice ages? Moving forward, I would like to flesh out my chronology by finishing and dating the rest of my samples on this large Pinedale Ridge to get see if I can find any more earlier advances. I would also then like to date this large intermediate ridge and these innermost ridges to then get a view into the millennial scale variability of the Boulder Glacier. I would like to thank you all for your time and your patience and your attention. And I will now attempt to address any questions you may have. Thank you. Yeah.
Can you comment on the possible role of temperature versus precipitation in controlling some of these advances?
Oh, I definitely can. So, it's not to say that precipitation has no effect on a glacier. That would be innate. But it's just the fact that temperature pretty much trumps its impact on a glacier, that we feel these glaciers are essentially telling us what the temperature was more like rather than precipitation. Now, if you want to look at precipitation, I would recommend looking at the lake records.
Mm-hmm.
All right, thank you.
It was so dark.
Yeah,
It was supposed,
yeah, I think it's the
that's
light.
why it was supposed to have a picture of the background. Hello, everyone. My name is Lívia Noveira. I'm here today to present my research, water quality in the rapidly changing environment of South Greenland. And my advisor is Dr. Paul Mayatsky. Next one. Yeah, so the overarching goal of my research is to develop a framework and also a baseline study in which we can assess future change in water quality and also water chemistry in South Greenland. Why is this important? Why is it important to assess water quality and also glacier meltwater pollution, especially in Greenland? Well, first of all, snow, permafrost, and glacier melting, they may release interact chemicals that some of them are essential to the ecosystem, but some of them are detrimental, including air pollutants. And that could harm human health, also ecosystem health that could impact the local agriculture, marine productivity, also the economy of the place and the cultural dynamics. In addition to that, we want to assess the influence of bedrock geology and watering rates, which of course will change with a warming climate and can also endanger humans and ecosystems. And well, I think as we all know, hydrogeologic regimes are shifting in Greenland, and total biochemical elements trapped in meltwater, they will increase with higher melting rates. Next one. How are we doing that? We are collecting water, surface water from lakes, streams, rivers, including also streams fed by glacier and seawater. And we are analyzing for isotopes, major and trace elements, or earth elements, and stable water isotopes here at CCI using our instruments and procedure. And we also have the PFAS samples analyzed in a different lab. I will present here today the preliminary results for 3 measurements. First one here is labs, then PFAS and isotopes. First of all, this is Greenland, this red triangle, not triangle, this square is our study area. This is the lab concentration. We divided into 4 categories. And we found that the concentrations, they ranged in seawater between 24 and 2,500 nanograms per liter, fresh water from 31 to 7,400 nanograms per liter. And 2 of these samples, they exceeded the World Health Organization guidelines, which is 10,000 nanograms per liter. An important thing here to mention is that the standards, they vary a lot according to different environmental agencies worldwide. And I will talk a little bit more about those. First of all, I already mentioned the World Health Organization, which is the standard is 10,000 nanograms. But there is also the US Environmental Protective Agency that they use 2 different standards. The first one is the MCLG, which stands for maximum contamination level goal, when they guarantee that there is no risk to health, which is 0. And well, it's not really realistic. There is also MCL, which is maximum contamination level, which is an enforceable standard. In this case, 15,000 nanograms. And the NZER, which is the Australian and New Zealand Water Quality Management Services, they suggest a safe level for seawater. Is the only agency actually that suggests a safe level for seawater, which is 4,400, and for fresh water, 3,300. One thing that I would like to point out that according to the US CDC, there is no safe blood level for young children. And the next step here is to analyze the samples for lead isotopes to check the different sources that from where all of this lead is coming from. PFAS. The samples, they were analyzed by Anatech lab, it's a lab in Idaho, and they analyzed for 25 different types of PFAS. We collected 16 samples. Out of the 16, 15 came from rivers and streams, 1 from lakes, which I will show you, and here's one here, right here, in the southern fjord. And this spot was the only spot that presented the 1 long chain PFAS, which is the PFNA, which is extremely toxic in the environment. And besides that, there were other 2 PFAS that we found, the PFBA, the yellow bar, especially found on the southern fjords, and also PFPEA that we found mainly in the north. And most important here is that we didn't find any PFAS within the communities. And all of the samples, they fell below health standards worldwide. And therefore, all observations that indicate that all of these PFAS, they have been transported atmospherically to the area. All right, so lastly here is the isotopes, water isotopes. Delta 18 and also Deltarium. This is the map. You can see here, it's also, we divided into 3 categories. Blue one is the most depleted, and the kind of hard to see here, but orange one, it's the most enriched. We can see here that isotopes, they vary. They have a high spatial variability in the area, but it's pretty clear that closer we get from the glaciers, we found the most depleted values, especially here in the southern fjords. And in this plot here, we can see that Delta 18 on the x-axis and Deltarium on the y-axis. And you can see on this plot that the distribution of the different types of freshwater samples, lakes, also snow, ponds fed by glacier, streams fed by glacier, and also the monthly precipitation from the International Atomic Energy Agency, that this data was collected in the interval of more than 20 years in a town nearby. And we can see some variability. The pink crosses, they are lakes, and they are more injected than streams. And the most depleted values, as I said before, come from glaciers, glacial meltwater. We will look deeper why we have such variability in the area, and especially here in Flower Valley, where we found the most depleted values, because we expected to find values even more depleted than those that we found. Yeah. To finish here, I would like just you to remember one takeaway from my presentation is that this is the first spatial characterization of the region's water chemistry and quality. And we intend to assess and also understand the local risks and the impact of atmospheric pollutants and also nutrient loads from melting of the Greenland ice sheet. And future work includes continuous sampling of a progressive river, Flower Valley. I will be back there in a few months to investigate how the chemistry varies throughout the melting season. Yeah. Last but extremely important, I just would like to acknowledge all of these people in these slides. Without them, I don't think this research would be possible. And thank you.
We have 2 minutes per question. Yeah.
I might have read the last graph wrong, but you showed that the glacier fed streams had the lowest variability, but it looked like the glacier fed ponds were way up at the top of the variability.
Yeah.
What's going on?
So it's an interesting story because we collected this water from the glacier. It was the glacier pond, which we thought that water would like come from the glaciers, but apparently that was actually rainwater.
Thank you for saying.
Yeah.
What do you think some of the sources of the PFAS in the area might be?
From what I was researching about this specific type of PFAS, they were actually very soluble in the atmosphere. So I would think rain, not moisture.
Okay.
Any other question? Thank you.
Read myself and my students.
Okay. Good afternoon, everyone. I am Alessandro Marghetti, and it's very nice to be in person to talk about this finally after a long time. I work in Japan Skill Lab, and today I would like to bring you back in time and a little far away in space to the Mammoth Steppe, which was the biome, like the largest biome in the world until the end of the Pleistocene, more or less. It was widespread across the whole northern hemisphere, and we know a lot of this environment. What we know today is that this place was kind of a mosaic of steppe, tundra, and boreal parkland. And one thing we know for sure, it had to be more productive than today's tundra or Arctic any biome, because it was brimming with megafauna that we don't see today, both as diversity and density inferred from the fossil record. This place has inspired renditions of beautiful landscapes. You can't see this side, but it's also very beautiful. You know, we imagine this kind of like beautiful field with mammoths and horses that kind of mimic what we see today in today's Serengeti, so much that it's been called the Serengeti of the North. And I think that I personally really like about this place is that it's been with us since, you know, we know of art, like these biome brimming with life, like was so awe-inspiring that forced kind of our ancestors, like Homo sapiens like us, to just portray and show these beautiful pictures that we can still kind of see moving with rhinos and lions hunting there. So much that people like Picasso went to these caves where this thing was recorded like 30,000 years ago and were left without words. Despite this, this biome is very charming, and part of its charm is that there's a lot we still don't know about it, despite it vanished very recently. Like we think about, you know, the onset of the Holocene, so 11,000 years ago. Part of the puzzle comes from the fact that it's so close to us, but we don't understand how it was possible. There's many outstanding questions, like what was the structure of this biome? We have this cave painting, we have plenty of fossils, but like how was the environment actually structured? Or like what was the balance of plants and animals? What were they doing seasonally? How are they moving on the landscape, right? Was this biome shaped by the climate or by his animals? And this is a question that gained importance in the last decades, because, you know, up to the 2000s, it was kind of, the understanding was that this biome was driven by the dry, cold glacial intervals of the Pleistocene. And so pretty much with the advent of that, at the onset of the Holocene, moisture drove shrub encroachment that led these animals that were supposed to be grazers to disappear. And that's the end of the mammoth step. But we know this environment lasted for literally millions of years across multiple glacial interglacials. So another interpretation is that the animals, as they do today, for example, in the African savanna, were drivers of ecological processes that we don't fully understand, and were able to maintain this type of environment, which would explain the surprising resilience of this biome across time and a very large extent of land. We also don't know why it disappeared, if that's the case, right? There's been plenty of interglacials, some warmer, some colder than today, but this biome showed persistence, and we don't really know when it disappeared. Of course, proponents of the climatic hypothesis think about the climate, proponents of the, let's say, biotic hypothesis think about the role of human hunters and Homo sapiens expansion. I'm not here today to talk about that, despite being very interesting. Of course, it's the kind of question that always buzzes in the back of your brain when you think about these biomes. As a paleoecologist, I am very interested in understanding the function of this system for many reasons. One of it is very interesting. The second is this actually has implication for understanding the resilience in today's Arctic and reintroduction of species that, for example, bison are trying to be put back both in Russia and in Alaska. So we don't know how these different herbivores were living together in a very homogeneous landscape, apparently from some depiction. It's supposed to be this like steppe grassland, but how diversity was able, if everyone was eating the same stuff. Ecology dictates that there must have been some partitioning of their feeding niche that we don't fully understand. How stable was this biome? Like, do we really know? Because there's so many things that we assume just because of the composition of the faunal assemblages, but we don't really have, for the whole extent of the mammoth steppe, a very good detailed picture of the biome, how it was structured. And also, you know, more details about the ecology of the single species. Like, you know, we know that they were grazers, but like, was a mammoth eating the same thing of a wild horse? When? Why? All these questions are left in the air, and there's many ways to investigate them. And the way I'm going to try to convince you that I'm looking at it today is by...
I can help you here. There you go.
Okay, by studying tongue. So I'm going to refer to the subfossil species that are left mostly in vermiforms as coprolites, even if they're not literally mineralized. But to me, this is super fascinating because it's very important to understand that what do we know about an environment is what we know today come from bones mostly, right? Or sediment records, which are not so common to find for older than the LGN, because, you know, most of the glaciers we found in the Arctic are very recent. And we want to go further back to understand the functioning of this ecosystem. Now, coprolites in that context give us a very high resolution of the plants, both taxonomically and temporally, of the plants that were eating, and so of the interaction that was happening on the landscape. Not only that, we can date every single coprolite and have a finite date, of course, if we're lucky with radiocarbon and we have no funding. But we can get a date for each coprolite and put them on a very specific space and time that allows us to ask questions about, in very high detail, about the functioning of a system that is long lost. To me, this is super fascinating. In particular, we can carry a lot of analysis for these coprolites. Today, I'm going to focus just on pollen and ancient DNA. This type of study is prime for multi-proxy analysis and interdisciplinary analysis. I don't have 2 hours and you don't have it. So I'm going to focus on pollen that is going to give us an idea of the environment because it deposits on the landscape and, you know, as an herbivore, you can eat it. And DNA that in this case is going to tell us the identity of the, you know, the animal that left behind the evidence that we're going to analyze. Yes, and despite you can see it, we're going to move to Siberia, in particular the Republic of Sakha. Back in 2019, we had the luck to be able to join a local expedition organized by the Academy of Sakha, back when the world was a much easier place to navigate. We went to the river in the Gurkha, one of these tributary, which I can't pronounce, is Tirkak River, where they find incredible specimen preserved in this rich, organic rich permafrost called Yaruma. They found lion cubs, which is like, this is like 20,000 years old, that looks like died yesterday, wolf head, because that's what they find. And thanks to Jacqueline, my advisor, a lot of coprolites. So today I'm going to present data from 36 coprolites from an area that is like, we consider the same size because of the way this animal could move, easily cover this area of like around 100 kilometers. We know that the whole assemblage of the mammoth fauna was there, and but we know that our coprolites are mostly mammoth, thanks to the DNA, with 2 bison and 3 woolly rhinos, and 2 reindeer or caribou, which are actually gut contents, which is a little different. We found the frozen carcasses of this animal and got the insides, but we'll talk about that a little later when we talk about interpretation. This is what we got, and we got this information because we're very lucky to be able to get this metabocotin locus, MAMP007, to actually tell us the identity of the animal. We are talking about samples that are older than the window for radiocarbon dating. So this was not expected, and we are super excited to be able to get DNA data. Now, talking about the time, the coprolite cluster in 2 intervals. One is pretty much the LGM, so last glacial maximum, coldest, driest period of the last, well, of the last glacial that we know about at least, or I know about. And the other one cluster around between 40,000 and, well, 55,000 and more years ago. We don't have a local climate record or local sediments that we can use for our biome reconstruction, but we can use models. In this case, there's this very cool package called Pastlin that came out last year that use very nice vegetation models, especially for the Arctics, and can derive annual mean temperature and seasonality and other things for specific location with a pretty high resolution. So this simulation at least show us that, as we expect, the annual mean temperature were dropping from this time bracket to this time bracket. So it makes sense to expect that the environment was changing, and it was, according to this model. Even if the model shows that it was supposed to be a shrub tundra, that's not actually what we see in our results. So we are talking about pollen. Can you please?
I would hope, yeah.
Thank you. Yeah, so these are, oh, might have done something wrong.
Don't worry.
Thank you.
There
Yeah.
you go.
So each of these donuts is a coprolite, strange as it sounds, and each of the colors represent a species in our pollen center. Now, just without thinking too much about the botany, green is grass, this golden yellow is forbs, and we have Artemisia, which is sage, it's like a dry indicator or like a step indicator, is this purple. And the rest, well, the rest is not so present. Like most of these sample look the same, and you don't need to eyeball this, right? First of all, this looks like a grassland, a steppe, which is not a dwarf shrub tundra, which is what the model was expecting, which is interesting. We don't need to eyeball to see, oh, these 2 intervals were the same. We can actually use something called non-metric multidimensional space to calculate the distance between each sample. So imagine that all the point, like I can plot each assemblage as a point, and the point in the space can be connected. Their outer sides can be connected as a whole based on their time bracket. And if, you know, this is a representation in a non-metric dimensional space of their difference between the samples, it's going to be much clearer in a second. If these spaces overlap, it means that the samples are pretty much very similar and time is not discriminant of these assemblages. If they don't overlap and they diverge, well, there's something that makes these assemblages different. The data shows that they actually overlap. So each point here is a coprolite, and the distance depends on the difference between samples. As you can see, LGM samples pretty much overlap with the LGM sample, and that shows some sort of cohesiveness, consistency of the environment across two very different time zones, which is very interesting. And to me, talk about the, you know, the not so important role of climate apparently into driving this assemblage. And we can do the same, but instead of plotting for plotting our half for the time, we can do it for the species because we have that information. So if these animal were using the same niche, the same, you know, ecological space, their niches, their halves would overlap, or they would like be apart if that wasn't the case. And again, the data, unfortunately, we couldn't pick what we found, but we have some information about how large the niche space of a mammoth is, and how, you know, these few points show that bison and rhino weren't sharing the same space. I'm running out of time, so I'm not going to dwell in the caribou, but I would disregard these points because the last thing you eat when you're starving is not necessarily a good indication of your diet. Let's put it that way. And these talk about an actual hint of niche partitioning, which pollen is not the best tool to use. So in conclusion, given this data, you know, the interpretation can be discussed forever, but like the hint here is that climate was changing over two different time periods, vegetation wasn't. And this support the idea of biotic interaction as a potential driver more than climate for the mammoth step, of course, in this location. The emerging picture is that mammoth has a broader dietary niche, while other animals were kind of, you know, more constrained, but we don't have enough point to talk about that yet. And pollen is limited. You know, we can talk about how can we interpret it, but the cool thing is that, you know, next year I'm going to bring you all the data from DNA and other stuff, and we can see how much pollen can actually be good as a descriptor of diet or not. And I'd like to thank you all for your patience and all these amazing people that made this possible and all these funding sources. And I don't think there's time for questions, but thank you very much.
We don't use 153, but I don't know if you want to do like 30 seconds of questions.
I will take any questions. You know. Yes.
So very, very nice talk. You probably can't answer it right now, but why do mammoths have a broader niche?
So very short, the bigger you are, the fewer high quality food you need. It's like you have a giant furnace, you just burn things and that makes you go. If you're a small animal that always need like food, you need to choose high quality food because you don't have space, right? And we see these in modern animals. I don't know, of course the question should be a lot longer, but this is a very small one. Thank you.
See the analysis since we're doing the brand. I showed some of that. It was like, come on, see.
Good afternoon. I'm Lizzie Gadrani, PhD student at the School of Earth and Climate Sciences, Climate Change Institute, and it's rare to talk something more pure after Alessandro's presentation. So today we're going to present preliminary results to define determination of concentrations in ice core samples using the laser ablation inductively coupled plasma mass spectrometry system, which was a system which developed at the Keck Laser facility at the Climate Change Institute University. So the outlines we're going to cover today are what is the laser ablation itself means. So we're going to talk about why robust ice core concentration standards are required. And also we are going to share with you what our interlaboratory preliminary standard measurements are showing. As an introduction, we want to answer the first question, what is the laser ablation? And in the middle of the picture, you see the laser. And what laser does, that shoots down into the window, and inside of this chamber, we're holding 1 meter of ice core, and we're moving the core and collecting measurements to the spectrometry you see behind of the picture. So it's a powerful analytical technology, and that enables highly sensitive elemental and isotopic analysis to be performed directly on the solid samples. And but when we're talking about laser ablation, we have to say why humane system is unique. So normally people in their instruments, they are not able to measure like 1 meter core as we do. They cut them in smaller pieces, and that's how they put to the cryocell. But the thing is that we can hold, here we can hold 1 meter ice inside of the cryocell in -20°C. And we also, that's the most charming what our system has, is that we can produce the continuous data, which is really great. So when research started on lasering ice cores in Maine, lots of experiments were conducted that demonstrated that it's really possible to convert intensity to the concentration of the ice we measure. So, but over the years, the process became really hard to accomplish because it was time consuming. And Sharon Sneed and Paul Majewski developed the methodology, and in early stages, they used the calibration from liquid samples to the frozen samples. And this is an example of how they developed this calibration in the first plot. And on this first plot, calibration curves are developed by measuring liquid standards, followed by laser frozen commercially available. One of the solution, they create a transfer function. Later, Nick Spalding improved this method, and she introduced simultaneous acquisition of several elements. And we see the short section of calcium here, data from the LICPMS single element method. I'm not the first person who started doing these experiments here, so this is like nice background to see what was before done here at CCI. So second question we want to answer is why is important to use the laser ablation. And we use this technology for Allen Hills blue ice area, but same time we're facing problem now because our concentration seems very low and very flat, and it's hard for us to separate measurements. And also I have to mention here that during the glacial signal we have really quite good actually data. But we want to understand better how intensities are related to concentration during the Imian interglacial. So we sent samples to Venice University and to Pascal, who is the co-author of this work. And he has a different laser ablation system. And he confirmed that his technology confirmed that the signals are very low. And he already was working on low concentration standards, and we took his technology and we adapted it to our system. And we wanted to see the concentration in Imian interglacial ice from Allen Hills, which is famous because of the this is the same site where the very old ice was found. And but the problem is when we make a standards, it has to be really perfect. It has to be homogeneous. If laser, for example, hits only these green particles during lasering, we're gonna get only one concentration. But if it hits the second, the yellow particles, we're gonna get another concentration. but when it hits the homogeneous ice, we're gonna get results that's compatible. And when we're making artificial ice, impurity is not always quite distributed, equally distributed. For ice core analysis, for laser ablation, it's not easy because standards need to be frozen and impurities has to be homogeneously distributed. So it's very hard to make ice that uniformly has the same concentration, because when ice is freezing, the impurities getting to the edges of the holder or whatever we use in the moment. And it's very hard to make ice that when we're freezing it. But when we make a good standard, the chemicals has to be well mixed. So when we ablate ice with the laser, no matter where we hit the material, we're gonna get same results. So we also having some kind of problems during our work. What's the major barrier here is that availability of homogeneous, low concentration frozen ice standards, or any standard with known levels of impurities. So now let's go over how the laser works in the great details. So we came up with a new way of freezing water, milk water. Here we present milk, 100 ppb, 300 ppb, and 500 ppb solutions, the concentrations. And so when we laser, we start lasering in the time 0 here. It takes about 12 seconds for signal to reach the instrument. Then we ablating 15 more seconds. And as you see here, generally levels are quite consistent, right? And with some minor variabilities, but lines are more or less straight. And when we stop ablating, signal deteriorates, and it takes about 40 seconds machine to finish its work. So what we do, we take signal from 12 to 60, 50, depends how the curve aligns, because this is not only this is not only one example or one process we did. This is like multiple times, and that's the latest data I'm showing now. So what we do, we take a signal from 12 to 60 seconds and calculating mean or median values. And this is what we use to calibrate our concentration to the intensity. This is like our goal on the end, to have like real numbers. And we see here copper, lead, and magnesium examples with the intensity, how with the regression lines with the concentration. So with that, I will be talking about our future directions. So one is that more experiments with the different concentrations, and we have to develop data processing routine and interpreting Allen Hills ice core LSE data. So we will be lasering ice core with the real Allen Hills ice cores, our samples, and publishing results. So this work will help me to measure an ultra high resolution signal of very old and highly compressed ice core records from the Allen Hills Blue Ice Area, Antarctica. And with that, we would like to acknowledge all sources of funding we had, and I will take questions.
Notice in your intensity graphs that the 300 ppb and the 500 ppb are most the same.
Yeah, so as I said, this is very beginning. So we're still trying to find the correct numbers with the big gaps between the solutions to get the exact number. But what we see here, whatever you saw, when we have a high concentration, it's really different, and it's like, they different each other. So we have to do multiple, I can say like more than 20 experiments to convince ourselves that it's working. And plus, yeah, and data is replicating every time. So this is work. Yeah, but thank you. We can discuss about this later. Thank you. Any more questions? Thank you very much.
So I think there's a question for Alessandro on the chat on Zoom. I'm so sorry that I didn't saw it. So Lauren was asking, are you surprised that Mammoth have a larger niche space?
Sorry?
Yeah, are you surprised that Mammoth have a larger niche space?
No, really. So I think this kind of in the same answer I gave before. Big animals have more choices about food, and elephants today can survive in so many environments because of that. Yeah. So I don't know if they can really do it.
Yeah, that's a good question. But thank you. So Hannah is not here in person, but she pre-recorded a video, so I will play that. And Lauren, if you didn't hear the answer of Alexandro, just let me know and he can share his answer at the end of this session. So let me see here. There she goes.
Good afternoon. My name is Hannah Brooks, and I'm a currently PhD candidate at the School of Earth and Climate Sciences. I'm excited today to talk to you about some work that I've been completing with colleagues at the University of Maine, Dartmouth College, working on the University of New Hampshire, in order to evaluate the effects of public policy and the COVID-19 pandemic on Asian emissions using elastic ice core data. Lead is an important tracer of anthropogenic pollution in the environment. It's released and evaporated into the environment through various methods, such as high production of industrial and commercial goods, combustion of fossil fuels, refuse incineration, chemical spills, and leaching and landfills. Early work on leaded gasoline indicated that during the combustion of fossil fuels, about 40% of the lead is released into the atmosphere as an aerosol. Once into the atmosphere, aerosolized lead particles can be transported along with naturally formed aerosols, such as sea salt spray, for long ranges, affecting areas as far as hundreds of kilometers from the original pollution source. In this simulation from NASA, we see the global distribution of aerosols from dust, shown here in red, biomass burning and fossil fuel emissions, shown in green, volcanoes in white, and ocean spray in blue. The distance of the particle being transported before deposition is the particle physical and chemical properties, including physical size, shape, mass, and composition. Today, we'll be focused on the North Pacific region, where the majority of the aerosols are transported across the Pacific Ocean from Asia to Alaska. Humans directly impact both the quantity and the source of these long-range aerosols, both in terms of biomass burning and fossil fuel emissions. Seen here are plots of lead emitted into the atmosphere per year through different pollution sources, from gasoline and coal and smelting for different Asian countries. So we can see here plotted China in pink, Japan in red, South Korea in white, and Russia in blue. This figure is from Kaufman et al. 2022. And what we can see is that there's been significant changes in these trends over time. So particularly with gasoline, there was a significant rise in lead as we had leaded gasoline additives. And then once leaded gasoline was phased out in 2001 in China and 2003 in Russia, we can see a dramatic increase in that emission source from gasoline. In other sectors, however, such as coal and smelting, we can see a general increase for some countries, such as China, as time has increased. Changes in trends are generally the direct effect of changes in culture, such as global pandemics, legislation, and technology. And this has been seen not only in Asia, but other regions in the world as well. The interest in lead has been a long result of history of extraction and use of lead throughout history in society for uses in currency and transportation, building materials. And then all the subsequent research that has come out of the severe negative effects of lead on human health. Lead is also interesting to research because it can serve as a proxy of other records. When we extract lead, we often concurrently release other trace metals such as mercury or zinc or nickel or at the same time. So before and after the use of lead as an additive in gasoline, it can be used as a proxy for other human influences in the environment. Additionally, it has been studied for a longer period of time than some of these other trace metals. So there's a significant number and decent global extent of paleoclimate records with long travel background atmospheric data sources. So at last count, there was 332 records of lead that have been taken across the globe. Really investigate how lead has changed over time. Additionally, lead isotope data is useful as a fingerprint for global pollution sources, as the ratio of uranium to thorium remains fixed in the ore body as it declines, and it's not modified at any point during atmospheric transportation of the aerosol particles. So in these plots, also from Hoffman et al., we can see plotted on the y-axis the ratio of lead 206 to 207, and on the x-axis 208 to 207. And in these fields, we can then see populations of Chinese aerosols versus aerosols in the United States, and other pollution sources end up plotting as cluster fields. And we can see how real data then changes over time. So this data is from the North Pacific. It's a collection of data from ice cores and snow pits. And we can see as the data gets younger, as it goes from yellow to the dark blues, we increasingly get less of a US aerosol signature as we go from panel A to panel D. Increasingly, we're getting more and more of an enriched Chinese source and a depleted US source in our North Pacific snowpack and basins. So for this project, we're using 5 ice cores that have been recovered from Uruguay or Mount Hunter in Alaska. The ice cores in question are the Denali ice core records, and they were reached. The first ice cores were recovered in 2013, and the record has been extended in 2019 and 2022. So now this record covers the entire Holocene through essentially the present. And this project builds off the previous work of Ben Gross and Eric Hoffberg and Bess Kaufman to examine this emerging story of pollution that's been deposited in the North Pacific from Asia. We can see plotted here in black the published lead concentration data from Eric Hoffberg's paper, along with the lead isotope record from Eclipse that Ben wrote published. And this work really aims to add an addendum or really investigate the most recent period by adding this section here in blue, expanding the work that Ben and Eric did, bringing it towards the present in the investigation of lead in the region. So in spring 2022, we melted all the ice cores using the melting system and ultra clean sample preparation procedures at Dartmouth College, sampling the ice every 20 centimeters. This means that we have now 1,070 samples spanning from 340 CE to 2022. Here they are waiting, sitting on the shelf. If you've been following along, you know that during this time period, CCI has a brand new mass spectrometer that came in. Here it is pictured. It's the new Element XR, which we're very thankful for the National Science Foundation for funding this new instrument. With this new instrument, we'll be able to more accurately detect low elemental concentrations, have higher sensitivity, and improve the isotope ratio detected. This is very important for the work I'm doing in the Denali ice cores, as it will allow sub-part per trillion level detection for lead. So I'm currently awaiting time on the machine in order to run these samples. But in the meantime, we are working to establish a new methodology to be compatible with the new instrument and the new detection limits we're now able to achieve. We have about an order of magnitude better detection limits on the new instrument. Therefore, we've been working to update the methodology we last ran 10 years ago on the Element 2. We've been running experiments to double check that our assumptions that our acidification is correct and that we are processing our samples adequately and that everything's clean enough. So this is an example of some of the methodology work that Mike Henley and I have been doing before we decommissioned the Element 2. We ran experiments on some real Denali ice on 31 isotopes, and we worked on 16 rare earth elements and 12 trace metals, plus lead and uranium, to see what the different response would be working at 10% nitric versus an HF solution. We found that occasionally, as you can see with uranium, you do get a better recovery with HF, as would be expected. But we ultimately decided not to continue working with HF. That the amount that it consumes your consumable and the additional risk of working with it was not worth the additional recovery that you paid. So this is the type of work that we're doing ahead of running the data set. So with that, I'd like to acknowledge the funding and all of the people who have been a part of this project. If you have any questions, I hope that you'll reach out and stay tuned for this data set as it comes out in the near future. Thank you so much.
Yes, sorry, computer is not accepting the password. There we go. All right. Hello, my name is Lauren Woods. I'm a second-year master's student working with Dr. Aaron Putnam. Today, I would like to share with you my work on addressing Mercer's paradox by comparing mid-latitude Brilliant 10 glacier chronologies. Throughout this presentation, I would like to attempt to convince you all that this folder is evidence that glaciers were not controlled by local summer insolation intensity during the last glaciation. The last glaciation refers to the period roughly spanning marine isotope stage 4 to marine isotope stage 2. During this time, mid-latitude glacier systems were achieving their most maximal extents during periods of high and low insolation intensity. This boulder sits on a lateral moraine at Soda Lake in the Wind River Range in Wyoming. The moraines at Soda Lake reveal a pattern of successive glaciations over the last 43,000 years. There's a similar pattern of glacial activity in other areas of the Western US and in the Southern Hemisphere. The main goal of my research is to address Mercer's paradox by constructing a beryllium-10 chronology of the moraines at Soda Lake in order to gain insight into the synchronicity of full glacial conditions and millennial scale fluctuations between the hemispheres.
You just tried to point it this way. There you go.
Great. Now we heard a little bit about Mercer's paradox from Xander, but I'll go over it again because it's pretty important. In 1984, John H. Mercer recognized that the Laurentide ice sheet in the Northern Hemisphere and South American mountain glaciers in the Southern Hemisphere were achieving their maximal extents around the same time, despite being subject to opposing insolation signals. Mercer's paradox is a problem because in 1941, Milton Milankovitch suggested that glacial cycles were driven by the orbitally modulated redistribution of incoming solar radiation reaching Earth's surface. According to this hypothesis, summer insolation intensity controls melt on glacier ablation zones, leading to advance during periods of reduced insolation intensity and retreat during periods of intensified insolation. Because the effects of orbital precession yield asynchronous insolation changes between the hemispheres, by the Murphy-Milankovitch hypothesis, we would expect to see glacier systems achieve their maximum extents at different times between the hemispheres. Mercer's study showed that ice sheets in the Northern Hemisphere and mountain glaciers in the Southern Hemisphere did not follow the patterns suggested by the Murphy-Milankovitch hypothesis. To evaluate Mercer's paradox, we are constructing and comparing comprehensive glacial chronologies for mid-latitude mountain glacier systems. A moment ago, I mentioned the Wind River Range, which sits at about 43 degrees north latitude, which is a similar latitude to the Southern Alps in New Zealand. This figure shows summer insolation intensity at each of these latitudes. We can see that both mountain ranges receive relatively the same amount of summertime insolation intensity, but on an out-of-phase basis. Based on the Murphy-Milankovitch hypothesis, we would expect glaciers to be reaching their maximal extents at times of low insolation intensity, marked by the dots here. Since insolation between the hemispheres is out of phase, glaciation between the hemispheres should also be out of phase. Numerous chronologies already exist from the Southern Alps, so it's our goal to construct chronologies in the Wind River Range so that we can accurately compare the two in order to address Mercer's paradox. My study area focuses at Soda Lake in the Wind River Range. During the last glaciation, a localized ice cap covered the Wind River Range with numerous lobes flowing out onto the base of the range, depositing many series of moraines, which you can see in the LiDAR imagery here. Soda Lake sits right next to Boulder Lake, which we just heard a little bit about from Xander. But the glacier at Soda Lake was a smaller distributary glacier that branched off from the main Boulder Lake Glacier during the last glaciation. Over the last 2 years, I have constructed a chronology of moraines at Soda Lake utilizing cosmogenic isotope dating. To create these chronologies, we combine field sampling and laboratory processing techniques to obtain the ages of glacial deposits. We start by sampling the surface of a large stable boulder on a moraine crest, on the crest of a moraine ridge. When these boulders are deposited by the glaciers, they are exposed to the atmosphere and constantly bombarded by cosmic rays. The cosmic rays react with the silicon dioxide atoms within the quartz grains in the rock and produce beryllium-10, which accumulates over time. Once we're back in the lab, we are able to isolate the quartz grains from the rock sample and extract the beryllium-10. Once the beryllium-10 is measured by accelerator mass spectrometry at Lawrence Livermore National Laboratory in California, we're able to calculate the age at which each boulder was deposited by the glacier and exposed to the atmosphere. Here is a glacial geomorphic map of Soda Lake and the surrounding deposits. Each of the yellow dots represents a sample that we collected during our 2021 or 2022 field seasons. These outer landforms shaded in green were deposited during the penultimate glaciation. Today, I'm going to be focusing on the inner landforms shaded in pink, which were deposited during the last glaciation. These two panels, which were outlined on the previous slide, show the exposure ages that we have obtained thus far. A majority of these ages come from this large outer moraine shaded in dark pink, also extends around on the other side, and from this innermost moraine ridge, also shaded in dark pink. These moraine ridges are large composite features that consist of several compressed and interleaving moraines. These ages represent the timing of glacial advance culmination. These boulders were deposited right as the ice left this margin and therefore indicate the last time the glacier was at its most maximal extent. The outermost ridge at Soda Lake records 4 periods of glacial advance culmination, starting around 43,500 years ago, 31,300 years ago, 27,500 years ago, and 23,200 years ago. The innermost ridge records 2 periods of glacial advance, culminating at 20,800 years ago and 19,900 years ago. Oh, there we go. This figure compares insolation intensity at 43 degrees north latitude with the timing of advanced culminations at Soda Lake. The most significant observation we can make of these data is that glacial advance occurred at times of both high and low insolation intensity. Based on the Murphy-Milankovitch hypothesis, we would expect glaciers in the northern hemisphere to reach their most maximal extents around 23,000 years ago. But these data show that the glacier at Soda Lake started constructing a moraine around 43,000 years ago and successively advanced to the same margin multiple times throughout an insolation cycle. These data defy the widely accepted hypothesis that summer insolation intensity controls glacier extent. But this is only one part of Mercer's paradox. The other part is the Southern Alps record. In the Southern Alps, there's evidence of multiple glacier systems achieving their maximum extents at times of high and low insolation intensity. This is the same pattern that we see at Soda Lake. And once again, these data defy the Murphy-Milankovitch hypothesis. When you compare the timing of glacial advance culminations at Soda Lake to advanced culminations in the Southern Alps, we find another example of Mercer's paradox. Each population representing glacial advance culmination at Soda Lake has a corresponding period in the Southern Alps. There's an obvious mismatch between the pattern of glaciation and insolation intensity between the hemispheres. We can make 4 major conclusions from these observations. First, as I stated before, moraine construction occurred in both hemispheres at times of high and low insolation intensity. Glaciers in each hemisphere were at their maximum extents and constructing moraines back their entire insolation cycles. This indicates that local summer insolation intensity is not sufficient to explain glacial advances during the last glaciation. These data deepen Mercer's paradox, showing that glaciers in both hemispheres were at their maximum extents at the same time, and that synchronous glaciation occurred between the hemispheres not just once, but multiple times throughout the last glaciation. Both of these systems indicate that the global climate system became stuck in a glacial mode early on in marine isotope stage 4 and was unable to exit this mode until the end of marine isotope stage 2 during the termination. One final observation is that mountain glaciers were achieving their maximum extents before continental ice sheets. This raises the question of the importance of ice sheet albedo feedbacks in driving glacial climates. The Wind River Range sits just southwest of the previous margin of the Laurentide ice sheet. If ice sheets were supposedly driving the climate and mountain glacier extent, then why is mountain glacier extent preceding the driving force? These observations show that full glacial conditions and millennial scale fluctuations of mid-latitude mountain glacier systems were synchronous between the hemispheres during the last glaciation. Before I open up to questions, I would like to thank the Comer Global Climate Change Foundation for funding this research, the Climate Change Institute for allowing me to speak with you all today, my committee members, and the many other people who have helped me along the way. Questions?
No, the next one.
Thank you.
Every word you said.
Awesome.
Thank you. There was an assumption in the past that it was true that northern hemisphere ice sheet, especially in North America, being so large that they're control global climate and the significant. And how would one go about demonstrating that that would not be at the level that would lead to the kind of status that we're seeing in more chemistry? I'm just asking because it's that's true that it's the northern hemisphere drives it, and we need to disprove it.
Yes, so that's
it had to be part of this way in some fashion. I don't think either of you really that.
Yeah, so that's a great question. Obviously, continental ice sheets are large masses of ice and can influence how wind belts such as the westerlies may be positioned during times of glacial climate or interglacial climates. So I think a way to start looking into that more is constructing more glacier chronologies from other areas in the United States or even in Canada, or even constructing more chronologies in places like Europe or in South America. There's been a lot that have been constructed. So I think really just nailing down the timing of glacial advances would really help in understanding the differences in glacial maxima between mountain glaciers and continental ice sheets.
And we need some modeling or something to remove that influence with the big ice sheet on these processes. Probably don't know what I'm talking about there. You know, the people have been saying that for a long time. They could and certainly those big ice sheets are important. But how do one demonstrate that they should not have had enough influence at these times?
I would say definitely some modeling would need to take place. But I feel like we need to have a full picture of what exactly was happening on a smaller scale to determine how it was being influenced on a larger scale. I wouldn't say I know much about modeling the climate in those conditions, but any other questions?
Hi, everybody. My name is Bailey McLaughlin, and I'm going to share some work from an ongoing chapter of my dissertation that I'm working on in collaboration with my advisor, Brian McGill, that I've titled, "Oh, the Places They'll Grow." And the key word here is really grow, because what I'm interested in understanding is where in climate space species occur, so that I might ultimately answer the question, do trees' climate tolerances differ across life history? The answer to which has important implications for how we understand species in their biogeographic contexts, how we understand their inherent ecologies, but also how we use that information in more predictive and applied contexts. And so, when I mention climate tolerances in the question I just raised, what I'm essentially referring to synonymously is the species niche. And in this context in particular, it's real-life climatic niche, which boiled down basically describes the set of climate conditions in which a species can survive. So what might that look like for an example? Well, if we simplify it a lot, we can take a hypothetical species and map its distribution in climate space, which I've done here in only 2 dimensions, but climate space can be n-dimensional. So my axes here are temperature on the X and precipitation on the Y, and this polygon represents the species niche, or the climatic niche, or the set of temperature and precipitation combinations in which that hypothetical tree can survive. And so this is important, especially because we often operationalize the climatic niche to make predictions or applications to management. And so we want to try to get this right. But
What happens if a species' climate tolerances change as it develops from a juvenile into an adult? Well, I'm glad you asked. There's some existing theory that starts to lay a groundwork for how we can understand potential life history differences in a species' climatic niche. So back in the 1970s, an ecologist named Peter Grubb described what he called the regeneration niche, which boiled down suggests that the juvenile life stage of a species has a more restricted set of tolerances than their adult counterparts. So let's see what that looks like. So for any given climate variable, for example, this could be temperature, precipitation, what have you, plotted on our x-axis and probability of survival on the y, we can see that the seedling survival curve in blue is more restricted than that of saplings in gray and adults in green, suggesting that there's a more restricted set of climates in which a seedling can survive when compared to a conspecific sapling or adult. Viewed a slightly different way, this hopefully looks familiar from the previous slide. If we map this distribution in climate space, again, our axes are temperature and precipitation, we can see that the seedling niche in blue is occupying a climatic subset of the sapling and adult niche. So importantly, whether or not this pattern is actually typical for most species is largely unknown and untested. But that leaves room to ask that question that I started us off with, which is, well, for trees, do climate tolerances differ across life history? And if they do, how do they differ? What is the actual pattern in the adult versus juvenile niche? And importantly, we can actually answer this question at large spatial and taxonomic scales using trees as a model organism, given their really long lifespans and really clear life stage classes of seedling, sapling, and adult. So to address this, I undertook what I'm affectionately calling a life stage niche mapping approach, where I took, for every tree in the continental US, I mapped its distribution in climate space for a seedling, sapling, and adult life stage. So to do that, I took geographic occurrence data from the US Forest Inventory and Analysis database, partitioned that into distinct life stages, which I plotted in geographic space. And then for each of these geographic points, I paired climate data from the World Clim database for 3 climate variables that we know are important to tree ecology, which are mean temperature of the warmest quarter, annual precipitation, and minimum temperature of the coldest month, which loosely translate to heat, frost, and drought stress. And from there, pairing the geographic and climate data, I can extract a 3-component climate coordinate for each point in geographic space to then map in 3-dimensional climate space along the same axes. And then you can summarize those with polygons or just plot their occurrences. So I'm showing you a lot of cartoons, but what does this look like with real data? Well, here are 2 examples of the distribution, the life stage distribution in climate space of a spruce and an oak along the 3 axes I just mentioned, in which the seedlings are represented by blue points, saplings gray, and the adults green. And I ultimately did this for 259 species. And once we map and describe the climatic niche in this way, we can then apply various quantitative metrics to evaluate differences between these life stage niches. So simplifying back to 2 dimensions for the sake of clarity of explanation, I'm going to go back to an example of temperature and precipitation as our axes and look at just one life stage comparison, which is seedling to sapling. So I'm going to walk you through some of the metrics we can use to try to quantify similarities or differences in the niche. One is changes in niche center, in the center of the niche along each climate axis. We can also look at changes in the maximum along each axis, changes in the minimum, and we can also look at changes in overall niche volume. And so in a little bit, I'm going to show you data from changes in the niche centers along each climate axis. But I just want to remind you that I did this in 3 dimensions and didn't just look at seedling to saplings, but also saplings to adults. So with all this buildup, I'm hoping you're now wondering, well, what patterns did you find? So before I show you the results, I'll start by giving away the punchline, which is for trees, the climatic niches seem relatively stable across life stages, which you might remember is not what our theory generally predicts. So this is what our preliminary results are suggesting, and I'll walk you through how we got to this point. And remember, I'm going to show you data from changes in the niche center along the 3-dimensional climate axes. So what we're finding when we look at those metrics is that niche centers appear to be pretty consistent between life stage comparisons. So again, the simplified metric, just to orient you to the data you're about to see, is change in niche center along each axis, but remember there's a third in my analysis. And we're looking at seedling to saplings and sapling to adult comparisons. So the first climate axis is change in minimum temperature of the coldest month on the x-axis. And on the y is the number of species. These are frequency histograms. The black line is centered on 0, and the dashed line is centered on the median of the distribution. And what you can see from these graphs is that the median is very closely aligned to 0, and that there's a pretty even spread around 0, suggesting that there's relative stability when we compare the seedling to sapling and sapling to adult niches along this niche centers along this axis. And the orientation of these graphs isn't going to change. The only thing that's going to change is the x-axis in the next couple of slides. So this time we can look at using the temperature of the warmest quarter. And what we see again is now you actually can't even see the dashed line around the median because it's exactly overlapping 0. So again, no real meaningful change along this climate axis. And finally, change in annual precipitation. Surprise, surprise, no real difference. And so I just showed you evidence that niche centers are pretty consistent between these life stage comparisons that we've done, which led us to the conclusion that there seems to be stability, at least when we compare centroids to the niche, across life history. Simplified back to 2 dimensions, maybe the pattern looks something like this. And I'll have to kind of just dangle this parrot, and you'll have to take my word for it because I can't show you the results from this project, but I've also extended this analysis into geographic space to look at life history differences in the geographic range of every tree in the continental US. And when we do that, what we're finding is that geographic range centers are shifting their ranges. And interestingly, those shifts are occurring in all directions, not exclusively towards the poles like we might predict. So for example, any given species might look something like this, where we have the juveniles in blue and gray. Their distribution is not aligning with that of adults. So when we put these 2 results in concert, what we know is that trees are shifting their geographic ranges, but they don't seem to be in all directions on these generational timescales that we can see from this life stage approach. But they seem to be largely tracking their climatic niches, which makes us think that the patterns we're seeing in geographic space are likely on, or could be evidence of incipient ongoing range shifts, and future populations could be where we currently have juveniles but no adults, because we don't think that these differences in geographic space are simply due to life history, given all the what I just showed you. So nothing happens in isolation. So there's a lot of people to thank, primarily Brian and my committee and lab groups, and all of you. So thanks. Any questions?
Quick question.
Yeah.
It was excellent and very nice presentation. Just wondering if you're looking primarily at the niche centers, are you also looking at the changes in shape of those forms on the graphs? And if so, is there a big difference?
So changes in sort of like the niche volume, kind of?
Even the actual shape itself, is there much of a change?
Yeah, so that's something that is still kind of in the works. So for the geographic project, when I map the geographic range, I take 3 different methods to draw those polygons because what we find could depend on that. It doesn't in my results. But for the niche, it's a little bit of a more delicate balance because it's 3-dimensional and so I haven't quite figured out a way to calculate volumes easily with other shapes, but I have looked at differences in the convex poles in 3 dimensions. And interestingly, saplings seem to have a smaller niche volume than either seedlings or adults, which again is not what we expect. So that seems to be like sort of the bottleneck or something, but still working on those sorts of things. And hopefully that sort of addresses your question.
Thank you.
Yeah. Yeah.
You say that your hypothesis was that you thought the mean would change based on the lifespan, but it did. Why?
Yeah, I mean, definitely a lot to think through still as this is kind of ruminating, but I think that that's a theory that we've had for a long time that we just haven't tested at large scales. So I would argue that we just haven't tested the theory enough to revise that. So I think maybe this is sort of a first step of saying, well, are these patterns happening? And definitely the work I do is mostly pattern detection, not really getting at the underlying mechanisms driving those patterns, but that's something I am in the process of thinking more about. Yes.
Seems that the trees are pretty resilient in that thing, but I would have expected that on the precipitation as relates to drought, that younger plants might be, but you didn't see that even on the drought index, if you will.
Yeah, not really. I know. It's definitely interesting to think about the potential reasons why. And I mean, one thing that maybe possibly gets a little bit at this is seedlings might be more vulnerable, but there's also typically more of them. Yeah, so I think they might be able to exist in a lot of spaces that they could survive in, but they can't for, competition or whatever, browsing or herbivory. Could be a lot of things driving that. But yeah, definitely puzzling. Thank you. Here. Yeah, okay. Okay. Hi, everyone. My name is Madeline Woods, and I'm a PhD candidate working with Kat Allen, doing paleoceanography work. And the major goal of my research is to create a temperature reconstruction of the Gulf of Maine that spans the Holocene. So from the present back about 11,000 years. So the Gulf of Maine is a really unique water basin because it's at the confluence of 3 major systems. So we have the Gulf Stream that is bringing warm, salty water from the south, and we have the Labrador Current that is bringing colder, fresher water from the north. And we also sit directly in the path of the westerlies. So we have, so changes in any of these 3 systems, which fill in the Gulf of Maine, can have consequences for water conditions in the Gulf itself. And it's also a relatively shallow system compared to other ocean basins. So atmospheric heat and also has a major effect. And we're seeing that as the Gulf Stream is moving more north and the Labrador Current is weakening, we're having a rapid increase in temperatures in the Gulf of Maine. We've had several years of seawater heat waves over the past 2 decades, and we're continuing to break seasonal temperature records. So actually the year that we went out and sampled, the Gulf of Maine was 5 degrees Fahrenheit warmer than average for that time of year. And these heat waves are being driven by global temperature trends. But in order to predict and manage the future changes that are going to happen in the Gulf of Maine, we need to understand the underlying ocean and atmospheric dynamics that have been operating here over the past several thousand years so that we can incorporate them into our models moving forward. So our short-term model warming trends that we've been seeing are not as useful as having long-term historical trends. So I have three overarching goals for this project. The first one, as I said, is to generate this continuous temperature record for the Gulf of Maine. Another goal is to estimate seawater oxygen isotope ratios in the Gulf of Maine to gain insights into how the North Atlantic Ocean circulation is affecting changes in the Gulf of Maine as well. So each of those water bodies that I was talking about have a specific isotopic signature that we can measure back through time to see how much of these water systems in the North Atlantic are influencing the Gulf through the Holocene. And lastly, but actually most important probably, is I need to field test the existing paleotemperature proxies that I will be using that were developed for deeper waters in the Western North Atlantic. I need to make sure that they are still viable and are giving us accurate, reliable results for the Gulf of Maine samples. So in 2021, we conducted a research cruise across the Gulf of Maine, and we collected a whole suite of samples. We went to every water basin we could find within the Gulf of Maine, really. We actually collected pores from 12 different sites and brought home 2 metric tons of mud that's now living at Bowie. And so we have lots of different sample types. We have multi-pores to get at the modern mud. We also have piston cores and gravity cores to get deeper through time. And the variety of samples that we collected really was to facilitate the calibration of the magnesium calcium proxy that I'm going to be using. To fulfill the paleo objective, we also collected several long cores that would have older sediments that hopefully would span the Holocene. So these are the locations of some of our cores, and we wanted to cover a wide spatial area of the Gulf because there are circulation and bathymetry dynamics at play in here that will affect our results. And so we want to be able to distinguish between regional or local or differences that we might find in our different cores. And so on the right here are some of the marine organisms that we use for radiocarbon dating these cores. So here are the radiocarbon dates that we collected, and we were lucky enough to have several cores that actually span the entire Holocene and some that even go back further in time. The colors match up to the locations on of the cores in the map there. Here we go. So you can see in our near core or near coastal cores, we have higher sedimentation rates, which is expected based compared to our more offshore cores. And this work is ongoing. So we have a lot of cores that we need to get through and a lot of material. So we have a lot of work coming up and a lot of things that I'm currently processing. So I'm establishing these species-specific calibrations. I'm also applying these calibrations down core into these different cores. I'm quantifying variability within the populations of these marine fossils that I'm studying. And I'm also analyzing additional elements to get at changes in carbonate ion concentration, which can have effects on the calibration. And on top of all of this, for the past several years, we've also been doing a lot of education and outreach work. So we created a mini docu-series that we just recently presented at the Science Festival, and that's what's going on here. In those pictures, I have actually 3D printed my little aquariums that that I look at under the microscope so that we can bring what we do into the classroom and into the public, because it's really hard to get more people out to sea. And so we're trying to bring the sea to people. And so what I really wanted to share with you today is part of that work that I'm really proud of. So this has taken years to complete, and we finally have a product that we can send out into the world and share with classrooms and all sorts of people that are interested in learning about our research. So I think you might have to press play. Yeah. So please enjoy this short little vignette. The way that we unearth information on ancient oceans and how they were changing is with a remarkable little creature called foraminifera. Foraminifera, or thoriums, are some of the most abundant fossils on the ocean floor, but you'd be hard-pressed to see them with the naked eye. Foraminifera. These are amazing single-celled organisms. They build shells to protect themselves. And those shells are about the size of a grain of sand, but they accumulate vast amounts of them on the seafloor over time throughout history. The warmer the conditions in which the foram grows, the more magnesium it takes up into its shell. If we can quantify that relationship in the modern ocean system, then we have a secret decoder ring that we can use to decode the fossil record. We can measure magnesium content of ancient shells, use that information to estimate past ocean temperature, which is really what we would like to do. There's a couple different ways to collect forams from the ocean, and we try to do as many of those ways as possible on our research cruise. So one of the main ways we collected forams is by using a plankton tow net, which is just a net that you tow through the water at a slower speed so that you collect the tiny organisms living in the water. It's the same way that Darwin collected plankton on the Challenger expedition. So we did that on this expedition because we wanted to capture live forams so that we had an accurate representation of the elements in their shells and the seawater properties that we measured at the exact same time. So when we pull up the net, it's been traveling underwater for a good 30 minutes. So it's skimmed a lot of water, and all those organisms that we think of as microscopic, we've collected in such a high concentration that it just looks like goop when we empty out the cod end of which is that plastic jar at the end of the net. All of that goop is some kind of organism or detritus from the water. So it's our job to sift through all of that gunk and find our precious forams. So we have to rinse out seawater. We try to filter out the larger organisms, such as shrimp or jellies that we've caught, and then we go down from there. We try to filter out the copepods, which are larger zooplankton. When we go down from there, we try to filter out the smaller phytoplankton that are way too small. And we're just sort of trying to filter and clean and filter and clean until we get to the shells that we want. And we do this as delicately as we can, because we don't want to break them. The plankton that we're catching in the nets are part of the modern material that we use in calibration. By looking at both of these things, by looking at the tow material, by also looking at what we call core top material, the modern sediment material, and looking at all of the information we have on the growth environment, keep all of that information together, that can give us a really good idea of what the things are showing us. So with that, I just want to thank everyone. If you want to know how to share or get a hold of a copy of that, please let me know. It's meant to be shared and distributed across our community. And of course, I couldn't have done this by myself at all. I want to thank my committee, everyone who helped me with the science and processing and lab work, as well as the media team that helped collect and make that video that you just saw, as well as the other ones in the series. So I'll take questions now. Thank you.
If you want to have a hope of understanding how the Gulf of Maine temperature changes over the Holocene, obviously you mentioned the winds, and the winds are what make the ocean do what it does in terms of that. So how are you going to get that? You don't have forams to tell you about the wind.
I don't have forams to tell me about the wind. So what we are doing is looking at how the Gulf of Maine is changing and then trying to interpret from that.
Oh, to backward forecast what the winds must have done.
Well, not necessarily the winds, but the North Atlantic itself. Okay. So focused mostly on the ocean. Okay. Yeah. I can't cover everything, unfortunately. maybe one day. Any other questions? Yeah.
You said there's a relationship between the magnesium content of the shell and use that to estimate temperature. What confidence level can you actually get a good temperature reading?
Yeah, so pretty good confidence, like within a couple of degrees kind of thing. So, but it really matters that you have a good calibration, and it's species specific and region specific. So the species I'm using has an existing calibration for different regions, but I think, as I mentioned, the one in the North Atlantic is from the Western North Atlantic, so pretty different conditions than what we might experience here. So that's why I'm spending all this time recreating a calibration before I even go down for. Good. Okay. Take a little hour
right now.
Yeah, interesting. Yeah. Cool.
Good. I think we're at time, so whenever you're ready, Andrea.
Cool. Yeah, so welcome back from snack time. My name is Andrea Terrell. I am a PhD student in ecology and environmental science and also the Climate Change Institute. I just recently defended my master's in the fall. So the work I'll be sharing with you today is the first chapter of my master's thesis, and then some like future directions, exciting stuff. So I work in New England's alpine plant communities, and these plant communities exist as small remnants or islands of the once vast tundra ecosystem, today surrounded by a forested matrix or sea of forests. However, the factors that influence the distribution of species across these sky island sites is unknown, and therefore their vulnerability under global change is also unknown. So after ice sheet retreat, New England was dominated by species that we now find at these high elevation sites. So things like stunted shrubs, herbs, grasses, and sedges. And as climate changed, these species were kind of pushed up to these high elevation sites. So today, what we see in most mountains, or some of our tallest mountains in New England, is this elevational gradient of different natural community types. So at lower elevations, so around campus, we might consider we would be in a mixed northern hardwood forest. And as we move up in elevation, we would see more coniferous trees enter the scene until eventually we would hit tree line, or some areas known as crummels. And then somewhere around 4,000-ish feet above sea level, we would enter the alpine zone, where there are no longer tall trees. Any trees that are there would be stunted, so would be crummels. And then those high elevation sites are dominated again by those grasses, herbs, sedges, and stunted shrubs. So I mentioned the idea that these natural community types could be considered islands. So I am curious about how the theory of island biogeography plays into the distribution of these species across sites. So what is the theory of island biogeography? It is this idea that the size of islands and also the proximity of islands to a mainland or islands to other islands affect the number of species that are present on an island. So you've probably heard, if you've taken an ecology course, about species area relationships, where larger islands may be able to house more species. And then there's this idea of extinction versus immigration from mainland populations, so that if a species goes extinct on a singular island, it may be recolonized by populations located on the mainland. So my main questions for this chapter included: what do geographic isolation, alpine area, and also topographic complexity, how do these factors affect species richness across New England's alpine zones? And then, are species distributions in New England sky islands in accordance with this theory of island biogeography?
So to try to answer these questions, I chose 8 field sites across New England, 2 in Vermont, so Mount Mansfield and Camel's Hump, 3 in the White Mountains, Mount Lafayette, Mount Pio, and Mount Adams, and then also 3 in Maine, Mount Abraham, Bigelow, Avery Peak, and also Katahdin. So this work required a ton of hiking, lots of elevation. So my methods in the field, I used square quadrats along each meter of a 50-meter transect to record species presence and coverage. Transect locations were either chosen based on historic transects. So like on Katahdin, we did a lot of work relocating historic transects and repeating them, or by establishing new transects at new sites in areas that were accessible. And in total, we did 38 transects during the summer of 2021, which totaled to 1,092 square meters of alpine vegetation surveyed. And so during these surveys, just to get an idea of what we're recording, species percent coverage is usually recorded by using the palm of your hand as a reference. So within that square meter quadrat, 1% is usually the size of your palm. So in this example, the diapensia here might take up about 40%, whereas rock is taking up about 60% of that quadrat. So to test the relevance of island biogeography theory within the system, I calculated the area of each of my field sites using USGS topo maps. And then I also calculated a connectivity metric. And to do this, I created a 10-kilometer buffer around the center of each of my field sites. And then I measured the size of alpine areas that fell within that buffer, excluding my field site. So this is an example. It's not super clear because of the lighting in here, but this is an example of a really heavily connected site. So this is in the White Mountains. This is Mount Adams. So Mount Adams is surrounded by a ton of other alpine areas, whereas somewhere like Mount Abraham in Maine is relatively isolated. So after those calculations and after fieldwork, I used generalized linear regressions to build models to assess the relationship between species richness at my sites, connectivity and area, and then I also had a separate model for some topographic features like elevation and slope. And so just to kind of be clear, when I say species richness, I'm talking about the number of species at each site. But I also decided to limit my species richness to alpine specialists, which are plant species that only grow in the alpine zone. So they're totally limited to those like patchwork sites. Whereas there are some species of lower elevation alpine ecotypes that do grow in the alpine zone, but also at lower elevation. So I excluded those from my model. And here's just some beautiful examples of some of the plants that we surveyed. So if you work in the Arctic, a lot of these species can also be found in the Arctic. They're circumboreal, so send me a photo if you see them. Yeah, so to get into some results, we found that elevation was positively correlated with the number of alpine specialist species, which is pretty intuitive. The higher you go up on the mountain, the more alpine specialists you're going to see. We also found a similar relationship with slope, which again, I think is kind of intuitive, where the steeper slopes were home to more alpine specialists. And then to move on to the idea of island biogeography, again, here's the relationship with connectivity. So we did find a positive, significant relationship between connectivity and alpine specialist species richness. But this part is what is surprising to me. We did not find that significant relationship with area, which is, yeah, totally surprising and unlike a lot of other Sky Island systems where similar research has been done. So to summarize that, the number of alpine specialists increased with elevation, slope, and connectivity. So there were more alpine specialists in sites that were in close proximity to a lot of other alpine zones. And the higher in elevation you go and the steeper slopes, we saw more alpine specialists. But area did not have this significant effect on alpine specialist species richness. So I have a lot of ideas about why that is, and I won't get into all of them. But so connectivity or dispersal between peaks and topographic complexity are impacting alpine species across alpine zones in New England. However, I think there's a lot of other factors that are playing into the distribution of these species, things like hiker visitation, human disturbance, climate change. But I think it's really interesting that these results might indicate some resiliency within these plant communities, because connectivity is impacting the number of alpine specialists at sites. We might be able to say that dispersal between sites can guard against these local extirpations, like I mentioned in the beginning. And so some fun and exciting future directions. We completed a resurvey of transects that were originally done in 1989 by Charlie, who's somewhere over here, and Don Hudson. So we'll be able to see if there have been changes in Katahdin's alpine plant communities through time, which is super cool. I'm also really excited to look into how to assess how increased hiker visitation is affecting these plant communities. And I also will be working with the Canadian American Center on campus to do some research about possible connectivities between Canadian alpine zones and New England alpine zones. And I forgot to put this on the slide, but I'm also excited that myself, Jacqueline, Aaron, and our undergrad researcher just had a paper accepted where the title is using photogrammetry to create virtual permanent plots in plant communities like this where permanent structures are not permitted. So yeah, with that, thank you to my advisor and the Peace Lab and everyone who has helped me with field work and analyses and our funding sources, the Churchill Exploration Fund and the Maine Outdoor Heritage Fund.
I think we have time for one question.
That was very good. Okay. So a question about the correlation between the slope and the result. Do you think it's because of the steepness itself, or maybe something like this position? Like we have powers of the southern or lower slope or stuff like that?
Yeah, so not in that model, but yeah, I think there's definitely more to it than just the slope of like the side of the mountain. I think aspect could have something to do with it. But also like slope itself would exclude a lot of species with like deeper root systems, like trees from growing in some of the like really steep areas. Yeah, I think there's a ton of different factors influencing where these species are able to grow, and this is just kind of like a glimpse, but yeah. Cool.
Hello, my name is Haley Manello. I am a second-year master's student working with Dr. Seth Campbell. And the research that I will be presenting today was a result of a expedition that myself and a previous student, Jonathan Maurer, had the privilege of going on in collaboration with a team from the University of Alberta, led by Kira Holland for her PhD dissertation work. What we've been working on our side of things has been the geophysical application. And so we led radar surveys here on the Quintino Sella and Seward glaciers. So this, if you are unfamiliar, this is
the Great Mount Logan, a super pretty area. So our study site here is at the intersection of the White River Kulani, Tlingit-Ani, and Veneta lands. And if you were at Keegan Bellamy, another graduate student's geo lunch presentation, she presented this really great resource called native-land.canada, which will give you information about the territorial extent of First Nations and Indigenous communities across North America. And it's a really great jumping off point for including the co-collaboration or co-creation of knowledge in the future of research. And so again, this is Kulani National Park and Reserve in the Yukon Territory. And so our objectives here were to characterize the near surface properties of the Quintino Sella and Seward glaciers. So we're thinking about things like density and liquid water content of the snowpack, as well as improve snow water equivalent estimates across this region. Now this is important because meltwater provides fresh water for over a quarter of the global population. And not only that, like the ice field to ocean linkage that we have from these freshwater melt fluxes influences things like the ocean dynamics as well. And so our estimates of snow water equivalent in North America have really high uncertainty, especially in regions that are mountainous and coastal, which is, if you can see again from our reference photo, exactly where we are. Oops, hold on. And then here on the right is a bit of a schematic showing what we would expect going from a, there we go. On the left here, a low elevation, coastal, warmer or wetter climate, we would expect, struggling for laser, some liquid water to be present in our snowpack. And we can study this with multi or common offset radar. But as we would progress up glacier or up in elevation, into a more continental climate, we would expect probably less liquid water to be present in that snowpack due to differences in mountain temperature. I'll take a brief moment here to talk a little bit about radar. If you're unfamiliar, it is a really, really excellent tool to study the stratigraphy of glaciers, as it has many different applications. But how it's working and what benefits us in this environment is that it's sending out a signal that will be reflected of layers of different electrical properties. And that's amazing because the different layers of our glacier we have here, so we have our annual accumulation, then the firn, so snow that's stuck around past the melt season that will densify into glacier ice, and glacier ice itself, as well as bedrock, all have different electrical properties, which allow us to use radar across many different glacier environments to pick out these features. And so our methods here to address the objectives we set out for were to speed tow a 400 megahertz ground penetrating radar system here, 60 kilometers from around 2,900 meters above sea level at Mount Logan Base Camp, down the Quintino Sella Glacier here onto the upper Seward Glacier to around 1,700 meters above sea level to try and get an elevational gradient or profile of what specifically Kira was looking at in isotopes and things, which also applies then for our snow properties. And so on this map here, this is the Mount Logan map tip, and our black track here just shows the traverse track that we took traversing these glaciers. The blue plot or the blue dots here are each of the different snow pits we dug to the first ice layer, not glacier ice, just a melt layer for those snow pit analyses for Kira's work. And then again, the elevation here is plotted also, but the colored tracks represent the centerline profiles that we were able to collect with this ground penetrating radar system. And so in addition to this, we also attempted to do depth density sampling in all of our snow pits. And so this is Kira and myself in one of our pits collecting some isotopic data. And so when we talk about radar data, the data, raw data that we collect comes to us in this in the form of time, so two-way travel time. And in order for us to make interpretations, we have to either make an assumption about how fast our radar wave is traveling, or have like ground truth estimates of that to interpret depth. And so one way I like to think about this is we're going to take a step back from glaciers and back from radar and put it into context of like, we're here in Maine and we're going to Bangor. The speed limit is like 70 miles an hour to get to Bangor, okay? So we might ask our friends, you know, like how long does it take to get to Target and back? And they're like 20 minutes. So that's our two-way travel time, 20 minutes. But, you know, those of us who lived in Maine over the winter have also driven on 95 when, you know, the signs are flashing 45, right? So the conditions change and it may take you like 30 minutes to get there and back. The distance doesn't change, but the conditions do, and therefore your velocity does. And so that was what also happens in snow. So the conditions that we're talking about are depth and density. And we just need to constrain that value by picking out a known layer that we have a known depth to. And in this case, we had a unique study where we weren't digging to anything that was super interpretable from our radargrams. So we decided to put something in the snow that we could positively identify, and that is a metal snow probe that instead of deploying it, you know, as it usually is to measure snow depth, we inserted it horizontally into our snowpack, which is a really fun and kind of scary endeavor. Don't want to bend it. And then we towed our radar over it in these small 8 to 10 meter sections. And I will show you the results of what this looks like in the radar, which I think is really cool. But this gives us an identification of a calculation of how fast that radar wave is traveling, and therefore we can determine or use these data to then figure out depths in other areas across the glacier, because this is time and energy intensive. So I'll share with you some results that we have initially. So this is a centerline profile or radargram that we have from our high elevation location. Here, this blue transect up here. And so for context, this figure, so we're showing depth on the y-axis here, distance on the x-axis. And we're going from up glacier on the left to down glacier on the right, so going down in elevation as well. And so some initial things that we can pick out from this radargram, I think are really cool. So like I was talking about, radar is useful because we can pick out layers of different electrical properties. And so that's maybe something like isochrones from significant snowfall events or melt. And so we see these great horizontal stratigraphic layers here, indicative of just previous snowfall. And then we can also, we wanted to initially interpret like what is the accumulation layer versus like the firn, so we could calculate snow water equivalence, but that's difficult because we have no frame of real reference here unless we were to have dug to that level, but that was not within our time constraint. Anyway, and then this is our second profile. This is the longest centerline profile we collected. So again, we're going same axes. We're going from up glacier, higher elevation to low elevation down glacier here, again, on the Quintino-Sella Glacier. And again, we see these really prominent, very cool stratigraphic layers. They do kind of get wiggly here. This could be from the terrain changing, like bedrock or different accumulation patterns. But what we observe is a decrease in that layering as we move down glacier, which is what we would expect. And in addition, while it takes looking into the phase response of the radar system, what we're seeing on the right here, it kind of looks like some vertical bands. This is characteristically similar to published work from our group from about 10 years ago, when you have liquid water in the ice itself. And so this is like scattering our radar signal. So potentially we're seeing more wet ice as we move down glacier. Oh, and I guess I'll go, oops, back, oh, too far, apologies. This was unfortunately the last centerline profile we were able to collect because we had, although we had a very elaborate charging mechanism going on, unfortunately our battery bank failed in the middle of the field season, and so we only had a certain amount of battery left. So myself and John decided that we were most interested in seeing what's going on at each of these Brown Creek locations, and thinking about what's the water content like in the snowpack early in the season. So like I mentioned, we put this like metal object into the snowpack, and it shows up really great in our radargram here at the vertex of this hyperbola. And so we can understand or take this two-way travel time and convert it to depth. I won't bore you with the equations, but what we get is this metric that's used to describe velocity, but I find this a lot more interpretable than doing something in meters per nanosecond. So this is a number of relative permittivity, just describing how fast or how well an electromagnetic wave can propagate through a medium. And so what we observe is that across our elevation gradient and our transect, there really is not much change. This is within our bounds of uncertainty, which is a really interesting thing to pull out, because like I mentioned, this property is affected. So the conditions that are affecting it are density and water content, and that's affecting our velocity and relative permittivity. And what we take from this then is that this is probably a very dry snowpack. And that's really, really a cool thing to observe, since for reference, the bulk of my master's work focuses on the Juneau ice field, which is a temperate and coastal ice field environment. And what I'm displaying here on the right are these same relative permittivity values, but this is in July, of course, different than in May here, but across a spatial and elevational gradient as well. And there's much higher variability between these metrics, and we interpret this as much more variability in that water content spatially. So, great one. In conclusion, we don't see any sort of elevational or temporal trend in this relative permittivity or water content. And the depth to the glacier ice we can probably interpret to be around 5 to 30 meters across the 2 transects that we were able to collect. Future surveying recommendations are to use GPR again to do continuous transects across the equilibrium line altitude. And this is because we're able to then trace those layers of firn up glacier from the ELA, and then also to do some form of multi-offset radar data collection, which will tell us more about continuous measurements of this property of water content across the glacier. And I would like to sincerely thank the Dan and Betty Churchill Exploration Fund, the Robert and Judith Sturgis Family Exploration Fund for funding both John and I to be a part of this expedition, as well as the Maine Space Grant Consortium and the Mount Logan Ice Core Project, University of Alberta Canadian Ice Core Lab. And then finally, our whole field team, myself, Kira, Darren, John, and Pierre. So thank you, and I'll accept any questions.
You went in May.
Yeah.
Were you getting any warm days? Were you thinking a lot of water getting into the snow?
Yeah, so once we got to the lower elevation onto the upper Seward Glacier, we were starting to get like warmer days. Nights were still very, very cold. But at our last site, we tried to take air temperature measurements as well, because we were starting to be curious about the effect that might have on this property that we're measuring at our ground truth points. And so what we conducted were 1-hour surveys, identical surveys, and measured both air and snow temperature. And from that, the air temperature just dipped slightly above freezing. It certainly felt a lot warmer, but maybe it's all relative. So I think perhaps some days on the lower elevations, you're getting above freezing, but not terribly much that I can recall empirically from most of the other sites. So. Thank you.
Is that?
Oh, no, podium. Bottom right.
Next to the little slider ball, just to the left of it.
Oh, yeah.
See the little, yep, got it.
I'm Suman. I'm a PhD candidate in anthropology and environmental policy, also associated with Climate Change Institute. I also work as a social science researcher at Himalayan Conservation and Research Institute back in Nepal. So today I'm presenting one of my chapters. So I just started writing a chapter. So based on my outline, I'm presenting it today, and I hope that this presentation will help me write my chapter. So I'm talking about the biophysical and sociopolitical vulnerabilities of case study from towards one of the most climate vulnerable regions, currently Nepal. So this is my quick outline. So I have a broad opening today. So talking about climate change, it's an undeniable fact. We know everyone about the climate change. So we know how the temperature is changing these days, how the water or the precipitation or rainfall is changing these days. So we have a clear idea about climate change, and also the recent publication, IPCC, the sixth report says that, what is the situation of we human beings passing with these days, and what is the future prediction of the human beings in 2020 in 2100. So the second picture shows clearly how the temperature is rising. So also this report has several other interesting images that shows how the scenarios in the temperature changing with different degrees Celsius, like, so it has like 1.5, 2.5, and 40. So how is it going? So it's like, so in the climate change. So it's an undeniable fact. So how is climate change impacting the people living around the world? So I argue that it's a difference of impacts. Different people, a different country, if everyone is facing climate change differently. So in case of a developing country, because I'm talking about Nepal, so how the mountainous country, Nepal is a mountainous country, we know that. And most of the people, around 68% of people are still dependent on agriculture and natural resources for their daily livelihood. So as a mountainous country, the mountains in the north are rapidly melting. The fragile mountain ranges or the hills in the mid hills of Nepal are facing different calamities, for example, landslides or soil erosion. It's like every year basis. And the lower plain, the southern part of Nepal, it's like a plain, and the flooding, the floods have been hitting the southern part highly. And climate change doesn't have only biophysical impacts that I'm talking about. It also has the socio-political impacts. How is the social, political, and economic aspects or the dimensions of a country or of a community matters the vulnerability or climate change? That's what I'm going to talk about. Because, most of the people living in poverty, most of the people from the low caste, or in terms of gender, women, or so these category of people who live in the marginal areas are highly affected because of climate change. So the vulnerability is more in these regions than other, where the wealthier people or where the people with greater access or political power live. So this is what I'm talking about. So here, these pictures are like a cartoon picture, but it gives a real message, right? So first one is like the scarcity of water, and in the rural part, there's no electricity, or people have like some health problem. You can see the polar bear, no habitat, carrying the ice or trying to find a habitat. So these are some both biophysical and then the socio-political impacts of climate change. So climate change is a threat multiplier, right? Because we already have some threats or we have some problems, but climate change enhances these problems. For example, people living in the community where there's a dominance of the lower caste people, or the people or the women living in those areas, they face more impacts of climate change than the people living in the different part of the community where the rich people are dominant, so which I'll be talking in my result section as well. So the first picture here, so this is their house right now. So before they had a house here, but it was like a marginal piece of land. They were poor, they were from the low caste, and as the temperature and precipitation is changing because of the heavy rainfall in the monsoon, the landslide came and their house was lost. And then they had to be shifted to a different house, but they didn't have any resources. Neither they, so like 1 minute from here is the local government office. I was there for 10 months, and none of these institutions or, people are helping these people. So they are becoming more vulnerable these days. And so climate change, they were already vulnerable, but the climate change enhanced the threat, The same thing we can see here in terms of development, how the climate change multiplies the threat. So having this background, my objective of this chapter is to understand how the biophysical and sociopolitical vulnerability is happening. How is that impacting the rural farmers living in the Karnali region of Nepal? So for this, I try to use the theoretical concept of vulnerability. So vulnerability, we have been hearing this for decades. It's not a new topic, but I hope that this research will add some information on the scholarship of vulnerability. So this is really interesting thing. The vulnerability does not fall from the sky, because as I have talked about how the vulnerability is impacting the people living in the rural part. So it's not that comes from the sky, but it's multiplying the effect, or the vulnerability is increasing within the social, political, and economic dimensions, and at the same time, the biophysical dimensions. The vulnerability has a different meanings to different areas of study. For example, climate change, development, natural hazards, or whatever, So it has been defined within different meaning. So in my understanding, or in my study, I found that most of the vulnerabilities are more dominated by biophysical impacts of climate change or biophysical dimensions, So I want to add some more information about the socio-political and both biophysical using the integrated framework. So I tried to use the O'Brien's 2009 framework so that it helps me to frame an integrated framing of the vulnerability, so that I use the biophysical and also socio-political and economic dimensions to define the vulnerability. So my study area, this is Nepal. This is Nepal, a pretty small country. So this is my study area, the Karnali region, the most rural part of Nepal. So this is my study area. So this question came into my mind while I was in Nepal for 10 months. So Karnali receives the special attention from multiple organizations, and also the climate finance goes into these areas. But this region remains vulnerable forever. Why? So this was my question that came into my mind. So a brief discussion about this study area. It is the remotest region. They have the lowest SDI among all 7 provinces. The annual economic growth is the lowest, so 5.7% of the entire. And the poverty rate is like around 51%, and 28.9% are absolutely poor there. The illiteracy rate is 40%. Ethnicity is dominated by high caste people. They are Kshetris and Thakris, and the political access is lower because the current federal government doesn't have any ministries or ministers from this province. The geography is cursed. It's a crazy part of Nepal, very tough geography here. So talking about methodology, I did the ethnographic field work for 10 months last year, starting in October 2021 and ending in the 2022 August, July. So I was there for 10 months. Before that, in 2019, I did like 2 months exploratory field work. So starting with the participants observation, I was there for 10 months. I tried to attend the everyday activities of the farmers, and also I attended different meetings, and I organized by different organizations, local government, and all of them there. So I tried to see how the climate change is impacting those places for the different types of people living in the community. So that's what I was doing there for 10 months. And I did some household interview to understand how the climate is impacting the farmers living there. So in both terms, how the biophysical impacts was happening, or how they were vulnerable in terms of biophysicalness or sociopolitical dimensions. So I did the oral history to see the both biophysical and sociopolitical impacts of climate change. So how was this community suffering like 50 years ago and now? Because I used the oral history, like the participants were above the age of 70, so that they could give me some ground information, you know, what they faced about all these things. So I did that. And so I also did some focus group discussion and key information interview to understand the impacts of climate change. So I tried to understand some political or some institutional dimensions of climate change application, climate change, doing some key information interview, and then I used the in vivo to code my interviews and analyze the data. So I also use the climate reanalyzer. In addition to that, I tried to collect some meteorological data from Nepal, from the Karnali, Nepal, to see how the temperature and the precipitation of that region is changing for 30 years or more than that. So I was doing that, and currently I'm doing these things. So I'm doing my analysis work right now. So this is what I prepared from the climate reanalyzer. So these are the meteorological stations from the Karnali region. We have 29 stations there. And using the climate reanalyzer, I can see that the temperature of this region is an increasing trend. And if we see the anomaly, so it's like since 1997, the temperature has started warming, and 2016 was the warmest year. So these are some of the maps, which are not really clear, but this is what I prepared from the climate reanalyzer. So I'm going to work on GIS to make it more clear. So we can see the temperature of the Karnali region has been increasing. And if we see the anomaly, so I try to compare the temperature of 2001, between 2001 and 2020, between 2001 and 2022, with the 1979 and 2000, I see that the winter temperature is really increasing rather than the summer or the annual temperature. So that's what I found also. So these are some precipitation data and anomaly. The precipitation have become more erratic, but the precipitation seems to be increasing since 2014 or something like that. So 2021 has a greater precipitation, which was also the information provided by the local farmers. So I also tried to generate some information from the local farmers about how are these things changing. So yeah, and these are again the change in the precipitation and the anomaly. The precipitation of this area has not been changed a lot, but it has not been changed a lot. So if we see the anomaly, so I don't see like big changes in this area. So comparing to 2001 and between 2001 and 2022 with 1997 to 2000, so I didn't see a lot of changes here. But in terms of the monsoon rainfall, the rainfall has slightly increased. And in terms of the winter rainfall, there is no change at all. So based on these, I found that the farmers are really facing problem because of the increasing temperature, and the rainfall has not changed a lot, but the timing of the rainfall has changed a lot. So farmers are facing very erratic rainfall, and the farming season or the farming time and the harvesting time have changed by about 1 and 1.5 months, which is a big change for those people. And based on the farmers' information, they told me that around 40% of their productivity has been decreased in the past 30 years. And these days, they have a big problem with the insects, they plant a lot of onions and garlics, but these days they have no productivity of those things. And this has increased their vulnerability. In addition to that, the intense rainfall in the monsoon and the erratic rainfall has caused landslide, soil erosion, and these things. So now moving into the sociopolitical vulnerability. So we can see your picture. These. So these are the elite people. I was there, and then I was there for a long time. So I was engaged there. So, but there is ever existing disparity based on the caste, gender, ethnicity, political, and economic power, and that multiplied the climate vulnerability disproportionately in this area. So, especially the poor people, low caste people, and the women. So the economic vulnerability, I can see the economic vulnerability. So some people, they have nothing, and some people have a lot of access to land, and they have more resources, and this had enhanced the vulnerability of that area. And so I have a quick case story. So this is the upper part of the village where I was living, and this is the lower part of the village where I was living. So with the slope of the village, the upper part was high caste people and the lower part was low caste people. So what I found there is like the access to the information, the access to resources and institution, market and infrastructure was decreasing with the decrease in the caste. And the benefit sharing was really low at the lower part of the village and higher at the higher part of the village. And the meaningful participation and representation was almost zero in the lower part of the village. So so based on this, I also found that the climate vulnerability is more increasing the lower part of the village than the higher part of the village. So this is a crazy word, I know, the bulldozer terrorism. Also, it's called atanka in Nepali. So I try to relate this because we have been adopting these things for construction of the road or some other developmental work. At the same time, we are also using for the climate adaptation. But what it has created these days in Nepal is it has become a national problem. So it has created a negative impact. And I found that most of the places in the village, the lower caste people living in these marginal areas have big impact of these development or adaptation projects. So it really needs to be thoughtful in terms of policies and how this can be done. So my conclusion is that vulnerabilities are treated differently. So I found that most of the focus of vulnerability was more on the biophysical aspects rather than understanding what's happening in the socio-political aspect. And the socio-political economic vulnerabilities get less attention. So despite the high attention and flow of the finance, vulnerability is still increasing in this area. And my argument is that because the root cause of the vulnerability, the social, political, and economic cause economic dimension has not been considered in terms of climate change. So I argue that the integrated approach to the vulnerability is ignored, and we need that to make a good policy. So finally, acknowledging research exploration fund, I got 2 grants. Thanks for that. The CES distinguished research grant from the grad school, and Alpha Grant Research and grad student government, the Department of Anthropology. Also my advisor, Dr. Cindy Eisenhower, and my committee, Dr. Sen, and some of my friends, and the collaborative organization from Nepal, also my research participants. So these are some beautiful pictures. And if you have
okay, I think we're running behind enough that we don't have time for questions. So we're gonna start the next one right away.
This is so many more people in person than last year. That's wonderful.
More normal.
Yeah. So my name is Elizabeth LeClaire. I'm an interdisciplinary PhD student working with Dan Sandweiss. And I'm going to take this opportunity. Well, actually, I'm going to need the clicker. There it is. Never mind. Take this opportunity to describe the research program I'm putting together for my dissertation. And I have not defended my dissertation proposal, so this is sort of a sneak preview. But this project builds on work that myself and colleagues here at CCI have been doing the last few years, looking at long-term adaptation of human communities to the El Nino Southern Oscillation in the north coast of Peru. And my work is going to look more specifically at the influence of Spanish colonization on processes of community resilience. So the El Nino Southern Oscillation is an interannual oscillation that affects the distribution of sea surface temperatures and atmospheric circulation in the equatorial Pacific. And El Nino here denotes the warm phase of the oscillation. And these events happen every 2 to 8 years or so. And there's actually several different modes of El Nino, which are defined by different oceanic and atmospheric patterns. But I'm really only concerned with 2, which are the coastal El Nino and Eastern Pacific El Nino. And these are the close to the canonical types that we think about when we hear El Nino in the media, for example. They manifest in the same way on the North Coast, and they're virtually indistinguishable in the archaeological record. So both of these modes produce significant anomalous warming of sea surface temperatures along the coast of Peru that steepens the thermocline, decreases bioproductivity, causes massive die-offs and outmigration of cool adapted marine species. And those the warm temperatures also disrupt the atmospheric they disrupt the atmospheric stability over the coast. So the atmosphere is usually very stable, no rainfall. During these El Nino events, we get deep convection, intense rainfall over what is normally a desert. And this produces flooding and mud flows, and they can be quite destructive. Now, paleoclimate records show that ENSO has been active on Peru's north coast for the past 5,800 years, although the cadence of the oscillation has shifted through time. And archaeological research shows us that through millennia of experiencing these events, Andean communities living on the coast developed ways of preparing for and responding and recovering from these events. However, human communities of the North Coast were not monolithic, and they varied in their vulnerability to ENSO events. And this is very clear in the case of a powerful El Nino that devastated Peru's North Coast in 1578 CE. This was 46 years after Spain invaded what is now Peru in 1532. And it was the first major El Nino event that was historically recorded. And eyewitness testimonies that describe this event, as well as general historical knowledge, indicate that Spanish colonial policies really ran counter to traditional knowledge. And it inhibited or even prevented people from engaging in traditional responses and made the event far more disastrous than it might otherwise have been. Now, this is not a new hypothesis that colonization compromised community resilience to El Nino. However, my research seeks to reconstruct specific processes of resilience and how they were disrupted. And so I'm putting together an interdisciplinary study that combines data and methods from archaeology, history, geography, and earth sciences in a case study of the Lambayeque region, which is shown in the map here on the slide. And the objectives of this research are to first contextualize the long-term adaptation and vulnerability to El Nino prior to Spanish invasion, and then delineate how responses to the 1578 event departed from traditional patterns. And then I'll also be mapping out, reconstructing the 16th century landscape and its interactions with El Nino, with colonial policies, and with community responses. So to kind of do some preliminary work, I went to the Lambayeque region last summer, along with Dan Sanweiss and former CCI student Heather Landazuri. We had several goals with this work. One was to confirm the locations of the towns that were affected by the El Nino in 1578, which are shown in the red circles there. This partly gets into some work that Heather was doing with spatial modeling. So we needed to know the exact geographic coordinates. And indeed, some of our research indicated that some of the towns had moved after they were destroyed in 1578. So we wanted to also try to find some of those original town sites. We also just wanted to meet local communities, get an idea of what the region was like. This was my first time going to Peru with the pandemic. And then third, for me specifically, I was interested in assessing the research potential for the kind of program that I described a moment ago. So over the course of 10 days, we visited 7 communities that were represented in those eyewitness testimonies of the 1578 El Nino. We documented important public spaces and cultural institutions. We visited museums and archaeological sites and met with local archaeologists. And we also spent a bit of time looking for 16th century architecture as a clear way of determining whether towns were still in their original locations where they were built 450 years ago. But as I said, some of them we knew had moved. So we also sought out those original town sites, documented what kind of archaeology is still there and that's visible on the surface, and assessed the degree of disturbance, kind of trying to get a handle of the archaeological potential based on surface expressions. So through the work, we confirmed the locations of 5 of those 7 towns. 3 of them recovered in place. And we found that they're heavily developed today. If there is any archaeology there, it's buried under buildings and streets and is inaccessible to us. Then we found that 2 towns had been relocated, and we went to the original town sites and found that those are lightly developed today. So they may indeed have some archaeological layers from that event. And then we also learned, and then there were 2 towns that were inconclusive. We did not find any historic architecture, no other indications saying one way or the other if they had been moved or not, no archaeological evidence of original sites. But during the course of the work, something unanticipated was that we learned that 2 indigenous towns were also inhabited during this event. So those 7 towns earlier were what are called reducciones. They were established by the Spanish and settled through the forced relocation of indigenous people from where they had lived elsewhere in the valley. But this process of reducción was still in progress in 1578. And so we learned that there are at least 2 indigenous villages that were still inhabited. And this was a really important finding because it sets up the possibility of doing comparative excavations from different colonial contexts, looking at differences in El Nino impacts and responses. However, we also identified some potential complications. For example, the reducción of Tucumán Viejo, in my opinion, is one of the more intact, at least based on surface expressions. It was kind of on the top of my list of the place to go to. However, while we were there, we found that the ruins of the church of that town are now used for what I will loosely call informal burials of what a collaborator described as very young children. This is a cemetery not associated with a church or a municipality or anything. So obviously inappropriate to excavate in the church, or in the ruins of the church, but also potentially there might be some sensitivities about excavating anywhere around there. So this is going to require some more work on the ground, some more coordination with the communities to evaluate not just the physical side of archaeological potential, but the social and cultural side. What is appropriate for us to do? And along these same lines, I really want this to be a collaborative project with local communities. So for the next field season, which I have 2023, but I learned this morning is probably going to be more like January 2024. I'm going to be doing interviews with community members. I'm going to be hopefully doing some more field reconnaissance, maybe find those 2 sites or towns that we didn't get any conclusive data on before. And then also visiting historical archives in the region to gauge their potential for some of the more documentary aspects of my dissertation. So with that, I'd like to give special thanks to the Robert and Judith Sturgis Exploration Fund, as well as the McGillicuddy's Community Center, National Science Foundation, and also all of the individuals who traveled with me, Dan Samwise and others in Peru, who were incredibly generous with their time and their knowledge during this work. Take any questions?
you've been through evidence on your site, but you kind of made this broad overbreaking statement about Spanish colonization. So do you have references to other sites outside of Peru where Spaniards colonized that, you know, similar?
So yeah, my research is very much focused just on the north coast of Peru. I'm also very interested in a completely different region in the Mariana Islands in the Western Pacific, where Spain also colonized and did the whole process of reducción, and they're also impacted by El Nino. But there is so very little work that I wouldn't even know where to get started there. But could be an interesting comparative case in the future. Yeah. All right, I know we're running behind, so.
Hello, everybody. I'm Scott Braddock. I'm a PhD candidate here in my lab here, working with Seth Campbell and Dr. Brenda Hall as well. Much of my work has been focused in Antarctica, looking at past climates and how glaciers behave. This is a bit of a detour from that. We're going to be focusing on a project from Alaska. There's a little video here. This is a very dynamic place. This is in the Alaska Range. This is where basically the planes are picking us up in the Kahiltna Glacier, or one of the ports. You can see a lot of avalanche debris. There's a Serac ball going on as this plane is picking us up to get rid of our team and bring us back to Talkeetna at the end of the season. So yeah, I just want to show this as a very dynamic place. It's changing, glaciers are retreating like in many parts of the world. We had a great field team, and this work couldn't have been possible without the Robert and Rita Sturgis Family Foundation, as well as other sources of funding. But in the true spirit of the CCI, this work builds on another project that started over a decade ago. And that work was started with Seth and Carl here and other students. And they worked on the same glacier in Kahiltna and collected data that we went ahead and repeated for this project. So the motivation, if we take a step back, big picture, the majority of sea level rise in the 21st century has been attributed to mountain glaciers. But with that comes some uncertainty. And a lot of this has to do with glacier mass balance, which is the budget between how much snow is accumulating and how much is lost every year. But in our estimates of how much is lost, we're not sure how much is actually being stored within the glacier itself, whether short or long period term, or maybe is being refrozen altogether and not transported out to the ocean. And I'll go into a little more detail about Fern on a different side, but Kaylee did a fantastic job in her talk of setting up kind of the problems we're trying to address here as well. You'll see this is another centerline profile of a glacier. This is the Alaska Range here, the Mount Denali is there, and then that red transect is where we towed our radar setup. On the right, here's an aerial photograph of Denali. This is the West Buttress route. It's very popular for teams heading up to the summit. And we flew into base camp around 1,700 feet and then followed that red line up to Camp 2. So this was a bit of an opportunistic trip. I joined a team that was flying up the Baguia Plateau. You'll hear Emma talk about that shortly. And on our descent, after acclimating from Camp 2, we were able to collect this data. And again, this is a repeat transect going back to 2010 or so. And we made it from Camp 2 down to what they call Heartbreak Hill. And we didn't go up that hill with the radar. We were good. I did want to mention there are several names. The Kahiltna is kind of an interpretation for one of these other names that were originally there for this glacier. It comes from one of the languages of the Athabascan people, a group of people that live in this region. So like Denali, this is one of the original names that's been interpreted for this region. Here we're working. So why the Kahiltna Glacier? This is the largest one in the Alaska Range, and it spreads over a long distance, but also a really large elevation transect, over 3,600 meters. Within this, over a shorter distance, we can capture this transition that Kaylee was talking about, going from colder, drier at higher elevations to warmer and wetter snowpack and fern pack at lower elevations. So we're all aware of snow that falls every year, but any of the snow that survives that summer melt season and is then buried again by the next year's snow year, that becomes firm. So that's the word I'm talking about there. It has a little less air in it, is a bit denser, is that transition between snow and ice. And because it has these pore spaces in it, it can retain a lot of water. So that's the question we're trying to ask both Kaylee in different parts of Alaska as well as here on Denali is how much water is being retained and at what elevation are we seeing that transition from warm and wet to cold and dry. So this dashed line here, this is a picture of the Kahiltna Glacier as we flew off. You can see this blue ice that we're all accustomed to, no snow covering, a lot of crevasses, and you're seeing this snow layer over that ice. So this line will transition up glacier and elevation throughout the summer. We ski towed or snowshoed our radar gear. This is our rope team here. A couple of the members, Inga number in the room, they'll be talking right after me. We did this on the descent so we can actually control the speed of the radar better. It's connected to us in the rope teams. On the sled itself, we have an antenna, which is the orange box that's connected with a cable to the receiver. So that orange box is emitting our radio wave, and then we can see in real time and receive the data that we're collecting. So we're actually getting what we want to see. In this case, we're targeting the upper about 40 meters of the snow and firn. So we have a shallow radar, but this gives us higher resolution at those shallower depths. So we're not seeing down to bedrock, for example. Another way of looking at this is the elevation profile, the transect. So the transect here on the bottom from Camp 2 right to the beginning of Heartbreak Hill. We go from about 3,300 meters above sea level at Camp 2, and then we finish down around 2,000 meters. So we've covered a huge amount of distance, well, rather not even distance, but rather a large amount of elevation over a short amount of distance. In this case, we travel 13 kilometers. The majority of that descent is happening in the first 6 kilometers here. And that's from about Camp 2 to Camp 1. Again, I'm gonna rely on Kaylee, did an awesome job explaining what these actual profiles that we collect are showing us. In this case, we have the depth below the surface in meters. We have an assumption here about the dielectric property that we use. We did not have any ground truthing on this trip, which is something that we're going to try to work on for this upcoming summer. But the main point to highlight here, something that Kaylee showed too, is that we have our cold and dry, the percolation zone, where we have the water moving through the snowpack. You can see that it's not really here because we can see beautiful banding going on, these different layers of isochrones that Kaylee mentioned too. And they're all distorted. This is extremely vertically exaggerated. We have 13 kilometers and 40 meters of depth here. But right around the 5 or 6 kilometer mark, where we lose most of our elevation, we drop down to around 2,200 or 2,000 meters. A lot of that signal washes out. It's just noise. And again, that's being attributed to the water that's within this glacier. We conducted the survey in June, so we're kind of in the heart of summer, not full melt yet. And we mostly traveled in the middle of the night. We would leave camp around midnight and finish up around 5 a.m. This was both for safety reasons, as well as to try to reduce the amount of water that we're picking up as a signal, because hopefully it's frozen. We're actually getting higher resolution at greater depths in that case. And I mentioned this goes back to work from 2010. This comes from a paper published by Campbell and Seth in the back here and others. This section of the transect that they captured from Camp 2 to Camp 1 is about 7 kilometers. So I pulled that 7 kilometers out of our transect as well. Ours was a bit longer, but that bold red section is about the same as what they captured in 2010. We had very different radar setups. They use a 40 megahertz antenna. So this is penetrating much deeper. So you get deeper penetration, lower resolution. You can see there's not much to see in the upper 25 meters, but you got absolutely beautiful stratigraphy below that. We're using the 400 megahertz antenna. So we're, again, only getting a shallow depth, but higher resolution. Some of the initial just findings here, there's a lot more work to do for interpretation, but it seems like this transition zone is about in the same place. Right around the 3 kilometer mark, we start losing or washing out our signal because of the amount of water content within the snowpack. Both of these were collected either in May or June, so similar time periods in the same place. I'm going pretty quick through this because I know we're short on time, but so some of the future work, we're going to continue to analyze those data sets. Keegan Bellamy is going to go out this year with a multi-offset system. She's going to repeat the same transect as well. She'll be giving a poster shortly after this. So if you got questions, she'll be out there. And using all these different radar setups, and over this time, we want to measure how much has the fern thickness changed. And then that gives us more information about that water retention in glaciers like this. And Kahiltna itself can act as an analog for much larger ice sheet glaciers around the world as well. So I'm going to stop it there. Just thank my team. There's Liam, Inga, and Emma. You'll hear from Inga and Emma very shortly. Thank you.
All right, hi everyone. I'm Inga Pinstead. I am a PhD student working with Carl Kreutz and Dom Winsky. And I'm going to give a little bit of a glimpse into some upcoming plans we have to investigate the relationship between snow accumulation and the behavior of surface melt at Eclipse ice field in the Yukon. But I'm going to do this by way of talking a little bit first about some of the work we did last year in Denali National Park, so building right off of what Scott did there. Just want to recognize up front that field work in Denali has been conducted on the traditional territories of the Dena'ina, Koyukon, Upper Kuskokwim, Ahtna, and Tanana peoples, past and present. And I'm going to throw up this map similar to what Scott was just showing, noting that Scott was talking about our GPR transect up in the Kahiltna here. And as he mentioned, we were running that transect as an opportunity to repeat a prior one, and we were also using that as an opportunity to acclimatize for some of our other science objectives for the trip, which were occurring on the summit plateau of Biguya. So once we finished up the work that Scott was just telling you about, we were bumped up to Biguya via helicopter. And Biguya is a great site because there's a lot of work that has been done there and is still being done there. In 2002, there were 2 surface to bedrock ice cores that Hannah has talked extensively about, drilled on the Biguya summit plateau that probably contain more than 10,000 years of climate history. The challenge, though, is that in order to interpret that history, we need to have a good idea of the age of the ice, and that is pretty difficult, especially at depth. So one of the objectives that we had was to go up there, do a bunch of geophysical surveying to develop age models to better constrain the age of that ice at depth. That's all I'm going to say about that. That's a little sneak peek because Emma's going to talk much, much more about the geophysics. The other thing that we did is we drilled a short core. So in 2019, some researchers went up and drilled a short core to bring the record up to what was at then present 2019. And we did the same thing last year in 2022 to bring that record up to present 2022. One thing that Hannah mentioned as well was the exciting thing that this covers the period of COVID. So you can see signals in that, which is pretty neat. Another thing that you can see here, here's an image of Liam, one of our team members, and he's holding on the left side of the photo, a section of core. And on the right side, this is a layer of refrozen melt in that ice core. I'm gonna step back and give a series of cartoons that you may have seen before, if you've talked to me ever, to visualize a little bit what goes on when we have surface melt on a snow-covered glacier. So here we have a column. This is representing our snow and fern column with our dark blue surface melt at the top. A lot of things can happen when you've got melt at the surface. It can percolate down to the snow into the fern and refreeze into a melt layer like we just saw Liam holding. And it might do that pretty near the top of the snow, or it could percolate much deeper and refreeze further down. Another option, especially if you've got a barrier somewhere in the fern, is you might get meltwater that starts percolating down, builds up, and then doesn't actually refreeze and is retained as liquid water in that fern. And if it's retained as liquid over year round over the course of the winter, we call that a fern aquifer. Another option is that maybe that water refreezes, but doesn't do so in like a nice discrete layer that you can visibly see. It might refreeze dispersed throughout the fern, in which case it's going to densify that fern overall, but you won't get those nice ice layers in an ice core like we saw Liam holding. And then of course, you can get runoff of your liquid water. So there's all these options of what surface melt can do, and there's a lot of open questions associated with them. And in particular, we don't really know with much certainty what the controls are on how deep does melt percolate, when does it refreeze, or does it even refreeze based on your conditions at your site. So last year we were up on Beguia, and we saw there were melt layers. There is some melt, but Beguia is pretty high. It's 3,900 meters above sea level. It's cold, and there just really isn't that much surface melt overall. So this summer we're going to another site, Eclipse Ice Field, which is about 900 meters lower and has more melt to look at. We want to recognize here that Eclipse sits in Kluane National Park and Reserve, and fieldwork there is conducted on the traditional territories of the Kluane, White River, Tlingit, and Champagne and Anishik First Nations, past and present. And then let's come back to all our scenarios of what melt can do. And I want to focus specifically on this fern aquifer, that liquid water. So that's kind of an extreme scenario, right, of your melt remaining liquid over the course of the winter. In order for that to happen, actually, I guess I gotta have kind of a captive audience here. So I'll pose it to you and give just a second to shout out an idea. What conditions might we need in order for that to happen, to have liquid water?
Pressure.
Pressure, maybe if you have a ton of pressure. We're talking pretty near surface environments here. What's the big one, the big obvious one for water to be liquid?
Salt.
Warm, yeah, it's going to be warm. But you know, we're not shipping the glacier off to Hawaii. So the next best thing we can do is to insulate these deeper layers from that intense cold that you get at the surface in the winter in the Yukon. And the way that those layers can get insulated is by a nice big snowpack. And so that's what's really motivating this question that I had in my title about the relationship between snow accumulation and melt percolation. Here we have an image of Eclipse. The green lines, there are some radar transects on here that were conducted back in, I believe, 2016. I just want to note this primary transect from A to A prime, because one of the observations that was made from that was that accumulation isn't constant over the ice field, which is great. It gives us a little bit of a playground. There's a bit higher accumulation up to the northwest at A prime, but a bit lower to the southeast. And so what we're going to do this year is we're going to go back and we're going to drill some more fern cores. And in particular, we're going to drill a cluster of 3 cores at each of those sites, in the higher accumulation site and the lower accumulation site, and see what we see in terms of melt features, in terms of meltwater alteration of the fern, in terms of little ice lenses that are discontinuous. And we're going to do clusters because melt percolation is notoriously heterogeneous. It's very spatially variable. And so we don't really know how representative a single core really is. And so we're going to do 3 within a meter of one another to see if we see the same melt features occurring in those 3 cores. Similar work has been done. This is from a paper that came out in 2021, where they drilled 2 cores on the Cascawelsh Glacier, 20 or so kilometers away. And this is essentially what our point is. We're going to look at stratigraphy. So it's all layering in those fern cores, noting ice layers, noting street ice lenses, and meltwater alteration of the fern. And they also measured density throughout their course, which is similarly what we're going to be doing. The one thing we'll do in addition to that is we're going to run radar transect between our 2 core sites, the high and low accumulation sites, in part to repeat transects that have been done there, and in part to specifically try to get a spatially integrated look at that annual accumulation layer and how it varies in thickness over that accumulation gradient on the ice field. This is our field team for the upcoming summer. So if you're interested in learning more about the questions we're asking at Eclipse, but are still listening to me, Emma is our queen of ice dynamics and geophysics. Keely is the resident expert in all things fern, if you haven't figured that out by now. And Renee is our go-to gal for liquid water in a glacier context. Also, just thanking all the other folks behind the scenes who have helped make last summer's work possible, as well as the upcoming work we're doing this summer. And I'll open it up for questions.
Time for one question.
Yeah.
So as you've been doing this for the past, at least since 2019, right? Have you noticed any kind of warming trend with more
Bigger layers of water or more spaces around water.
I've only been up to Biguia this last year. Eclipse is interesting because people have been up, not me specifically, but people that I work with have been up repeatedly. And so one thing I am personally curious about is to go up and bring back my observations this year and compare with like Carl and Dom and folks who have been up there, what they observed. But I don't have personal experience to speak from.
Do the meltwater aquifers happen at the bottom of the firn on top of ice, or do they happen in the middle of the firn on a previously determined?
That's a great question for a number of reasons. The one that I showed from that 2021 paper on the Cascades, so that was probably at the firn ice interface.
Okay.
But the question of can water build up on top of an ice layer and like how thick of an ice layer it takes to do that was totally open-ended, because in large part that really heterogeneous nature of melt percolation is sometimes you get like a really thick ice layer, but there's cracks in it until water doesn't build up.
So those aquifers are likely to be lenses, not going for miles, right?
Also kind of an open question. So there are aquifers in Greenland is the famous example where they're really, really widespread and extensive. Mountain glaciers, we just haven't sampled them quite as much. And so in the St. Elias and the Yukon, but that is something that I personally am really, really interested in, because there's a few sites where people have said, oh, there's a firn aquifer here, and it probably developed relatively recently. And so the question of how widespread they are and are they becoming more widespread is one that I would love to answer.
Thanks.
All right, my name is Emma Irwin. I'm a PhD student here at UMaine studying with Seth Campbell. And I'm going to build off of some of what we just heard about and talk about the geophysics survey that we conducted this past summer on the Biguia Plateau, which involves investigating the effects of ice deformation on the Denali ice core record. So we are in the Central Alaska Range, we are in Denali National Park, and we are at the site on the Biguia Plateau where the Denali ice core was drilled many moons ago. This is our field camp, which is pretty much right at the spot of where they drilled the ice core. From the ice core, there have been some really interesting results of late. This is provided from Dom Winsky and Carl Koitz. The stable isotope record from the basal proximal ice of the Denali ice core is quite variable. And that variability is really interesting and poses some big questions about what is the age of that ice, where we see that big dip in the stable isotope record. One possibility is that this is a stratigraphically continuous record that contains ice as old as the Eemian era, which would be very, very exciting. Another possibility is that there's some folding occurring at the site of the ice core, which is causing folded layers of Holocene and younger Dryas age. So the big questions motivating this work is number one, is the basal ice stratigraphically continuous? Number two, what is the depth age of the full ice column? The reason why we care about the Denali ice core is because it provides a really unique and insightful record of paleoclimate in the North Pacific region and the greater Alaska area. There have been several ice cores drilled in the greater Alaska region over the last few decades. In this past summer, 2022, several folks in this room helped with the Mount Logan ice core, which contains a record up to about 20,000 years old. The Denali ice core contains kind of the second oldest record, if it spans just the Holocene, but if it contains Eemian ice, that would be the oldest ice in the region. Our field team conducting this work, we've got Scotty B and Inga from the University of Maine. We also have William Kirkpatrick. He has his graduation cap. He kindly came with us on our field season instead of going to his graduation from Dartmouth College, and he's now a PhD student at the University of Washington, and then myself. Our objectives while we're on the Biguia Plateau, in addition to what Scott and Inga just told us about, were twofold. One was to characterize the Englacial stratigraphy, and then secondary was to quantify the depth age using geophysical data and incorporating that into a three-dimensional numerical flow model, which I'll be constructing throughout the course of my PhD. The methods for accomplishing both of those objectives include collecting a suite of geophysical data and then incorporating that into kind of modeling algorithms. And so the two different geophysics techniques that we use in this project are first ground penetrating radar, which Kaylee and Scott both showed us beautiful slides about. And then secondary is a different radar system called an autonomous phase sensitive radar, which I'll refer to as an AP-RES. So just like we heard earlier, radar units give us lots of insight into what's happening below the surface. We have an electromagnetic wave that is transmitted through the ice, reflected off of mediums of different electromagnetic properties. And then we're able to calculate the depth of those mediums when we make assumptions about density, and also when we're able to calculate the time that it takes for that wave to return. This is video that might not play, you can't really see, but to first some scale, this is another angle of the Paguya Plateau. We have our camp right here, we have very, very tiny Scott Braddock dragging some radar around. There's Scott Braddock again, dragging more radar, doing a lot of the heavy lifting for this field team. We use 3 different types of radar surveys up on the Paguya Plateau. I'll start with the shallow radar survey. So this is the same radar unit that Scott just talked about dragging up the Kahiltna, or rather down the Kahiltna. And on the Paguya Plateau, we're able to image isochrones down to about 30 meters in depth across the plateau. This is what one of those radar grams look like. The magenta line is tracing an isochrone or a layer that was deposited at the same time across the plateau. And when we trace that across all the profiles that we collected, we have essentially a spatial map of the differences in two-way travel time of that glacial reflector across the plateau. This is really interesting because it could be differences in accumulation rates across the plateau, which will be really important for integrating into a more accurate numerical model that is in 3 dimensions across this site. It could also be representative of changes in density across the area. And so that is something we're curious in investigating in future work as well. The second major radar system that we brought up to the Paguya Plateau was a 10 megahertz radar system. This radar system has a longer wavelength, and so it's able to propagate through the ice path and image glacial layers that are deeper. And so we use this radar to measure ice depths and basal topography across our survey area. This is what one of those radagrams looks like. We can see that the topmost section is pretty noisy. We're not able to distinguish what's happening there, but we have these very bright reflectors at the bottom for your evidence of the bedrock. The blue line is the kind of profile where the Denali ice core was drilled, and the red box indicates that it is pretty challenging to unpack what is happening in the bottommost section of that profile because of all the sidewall reflections. The basal topography is not flat in this area, which makes that a little bit challenging to unpack what is going on at depth. By picking out all the ice depth measurements from all the profiles we collected, we're able to create kind of a bed map of the area to supplement radar data that have been collected in years prior. And so this map shows those ice depth measurements, which have been interpolated using some kind of preliminary interpretation algorithms in Python. And the site of the Denali ice core is in this red diamond here. And then I've generated a 3-dimensional mesh of the basal topography just for reference. Again, this is a little bit rough, but we see that the Denali ice core site was drilled a little bit in this kind of like, not quite trough, but a little bit of a little bowl in the bedrock, which is interesting and will be really interesting to understand with a really high quality 3-dimensional model, what is going on with the ice at depth there. Is it trapping really, really old ice, or is it causing these layers to hold near the bottom of the ice core? The third radar system that we used on the Paguya Plateau this summer was the AP-RES. This is the structure that we used to tow this radar around, which was very well engineered by Inga. And this radar is really interesting and unique because it has a frequency modulated continuous wavelength. These properties allow us to image glacial features with sub-meter resolution, so a lot more high precision than the standard GPR. Using temporal repeat measurements, so taking one measurement and then repeating that measurement at the same spot over time, we can detect vertical deformation within ice facts. So we're not just able to pull apart a static image, but we can understand what's going on in the vertical domain and how it's changing over time, which is really cool. This is a cartoon of what that radar looks like. We have a transmitting unit and a receiving unit, very similar to standard GPR, but this time our wavelength is changing throughout the length of the pulse. By measuring the phase change between those signals, we're able to calculate the vertical deformation of a reflector within the ice. And we're able to do this at very high resolution. We collected a total of 22 measurements across the Paguya Plateau this summer. And then we waited 14 days. We played lots of cards. We waited for the ice to move, and then we went out and measured them all again. The bullseye is the spot of the Denali ice core.
So we collected 2 transects kind of in the north-south and east-west direction roughly. The exciting thing is that from all of those sites, we were able to measure some sort of vertical deformation of the ice pack. The reason why this is exciting is because while this tool has been used with great success in places like Antarctica, this was the first time to our knowledge that we were able to capture vertical strain rates in an alpine glacier environment, which is really exciting. This is what some of that raw data looks like. We've got a signal that's propagating through the ice pack. We have one signal that was captured on June 10th, and then another that was captured 2 weeks later on June 24th, and they look pretty similar. It's pretty hard to distinguish what's happening between them, unless you do a little bit of math and calculation. One feature that's notable though, is that we have an increase in power return near the bed. It's roughly around 200 meters, which is where we expect the bed to be. It's not very precise though, and we think that that's because there is some interference with some sidewall reflection of the sidewall reflections at that site because of the bowl feature. And so when we go back this upcoming summer, we'll be using some different measurement techniques to try to resolve a little bit more what's going on near the base. From kind of calculating the differences between these 2 measurements, we're able to calculate the correlation or the correlation magnitude between the measurements to make sure they align well with one another. Generally, using this measurement tool, a correlation coefficient of above 0.9 is considered pretty good. And so we have pretty strong correlation in the top 150 meters of the ice pack. Again, this is very exciting because this is a new environment for this tool to be used in. Unfortunately, for our question of what's going on at the bottom of the ice pack, it is hard to resolve the resolution of our signal in the bottom kind of 50 meters. Once we're able to use the strongly correlated signals, we can calculate the phase change between those 2 signals, calculate the vertical deformation, divide by time, and we come away with the vertical velocity profile that is shown in blue. By taking the gradient of the best fit to the vertical velocity profile, we're able, sorry, this is just a simple quadratic fit. But then by taking the gradient of that, we're able to calculate vertical strain rate. Right now, that's just a very simple kind of first shot at it. I'll be doing a little bit more math and a little bit more calculation to come up with a more sophisticated model that changes with depth, to then compare to a preliminary model that was based off of some geometry that Seth built in a 2013 publication and come out with a better profile. Returning to our questions that drive this work. First, is the basal ice stratigraphically continuous? Unfortunately, we have pretty low resolution in the bottom 50 meters of our measurements from last summer. So we have some more work to do, which we'll go back this summer using more techniques to try to unpack. And the second question, what is the depth age of the full ice column? Luckily, we have a lot of information that we gathered this summer. It is really exciting to have so many measurements of vertical strain rate across this area. And by using these measurements to constrain a 3-dimensional numerical model of the site, which I'll be working on over the next few years, that will potentially be the most highly constrained 3-dimensional numerical model of an alpine glacier. This work was supported by a lot of different funding sources, including the Robert and Judith Sturgis Family Foundation, and our 2023 fieldwork will be heavily supported by the Dan and Betty Churchill Exploration. That is all I have.
How far back in time can you use the vertical strain rates to estimate the age of the ice? Over time, does the vertical strain rate change, or how would you be able to predict this?
Totally, that's a really good question. So what I just showed was like very preliminary, where I just meant like a line, which pretty much just gives us a single vertical strain rate. That's an average over kind of our best fit. I will be doing some work to make that line not a straight line, so that we're able to see how it varies throughout the entire ice pack. So the goal is to get vertical strain rate profile this summer by measuring full year's amount of change. So we left a secret little marker at the site where we took this measurement. We'll go back after a year-long interval, which we hope will be able to tell us a little bit more about how the ice is moving at depth, so that we can capture more of how it's moving at depth and how that might differ from how it's moving at the subsurface.
All right, now we have 2 pre-recorded presentations.
I'm Ryan Miles, and today I'm going to be talking about my research on the glacial geology at Baxter State Park and in central-east Katana. First off, why study the glacial history of Katana? Not only is it conveniently located just a few hours on the road, but it's also the largest mountain in Maine. Because of this, glacial deposits span from the height in the last ice age, when ice covered the summit around 20,000 years ago, down to when the ice left the area, probably around 13,000 years ago. This about 7,000-year time slice that's preserved along the flanks of the mountain can give us important information about when and how quickly the ice thinned at the end of the last ice age. The end of the last ice age, also known as Termination 1, was not a smooth transition to warmer temperatures. It had multiple abrupt shifts in climate, as reported in temperature reconstructions from ice cores in Greenland and Antarctica. These graphs show oxygen isotope records with time on the x-axis and delta 18O, approximate for temperature, on the y-axis. There are three known events highlighted on this figure. The first is on Stadium 1, which spanned from about 18 to 14.7 thousand years ago. It's been interpreted as a classic stadial period in the North Atlantic region with extremely cold temperatures. The top panel of this graph shows these cold temperatures as reported in the GISC 2 ice core of Greenland. This contrasts with the Southern Hemisphere record in the bottom panel of this graph from the waist divide ice core of Antarctica. The Antarctic core shows warming temperatures during Hybrid Stadium 1, while the Greenland core shows cool temperatures. These cores also show an out-of-phase relationship during other climate events, such as the Millennium and younger giants. This conflict between hemispheric records has resulted in the idea of a bipolar seesaw, with thermohaline circulation playing a crucial role in the climate during the last termination. Wally Broker, in his 1998 paper, proposed that during stadials, or colder periods in the Northern Hemisphere, shutdown of the Atlantic Meridional Overturning Circulation, AMOC for short, just south of Greenland in the North Atlantic, caused a backup in this conveyor belt system. This resulted in a buildup of heat trapped in the Southern Ocean, unable to continue circulating through the system and disperse. This led to warmer conditions in the south, while the north remained cold. The figure on the right illustrates this idea. Warm southern hemisphere and cold northern hemisphere during stadials, like Hybrid Stadium 1, and the opposite for interstadials. The south is cold and the north is warm. However, recent data from other proxy records, such as the glacier geologic record, have cast doubt on this idea of a bipolar seesaw. The new data suggests that the hemispheres may have actually warmed synchronously during the termination. To get a better picture of the climate during the termination, I've begun reinvestigating the mountain to answer these questions. What was the rate and timing of ice thinning? Was ice thickening during Hybrid Stadium 1, as would be expected in the idea of a bipolar seesaw and a cold stadium during Hybrid Stadium 1? Or was it actually thinning in alignment with other proxy records? This is a digital elevation model from the LiDAR at the time. It's the largest mountain in Maine at 1,606 meters. It has 3 large cirques and several smaller ones. While these were likely filled with alpine glaciers prior to the last glacial maximum, previous work suggests that the speed of the termination didn't allow enough time for them to reform following the retreat from the Laurentide ice sheet. Therefore, during the termination, the mountain emerged up out of the ice as an unattacked, or a glacial island. This figure shows a representation of what the ice extent may have looked like around 16,000 years ago. Because of this emergence, the glacial record on Katahdin can be used as a dipstick to reconstruct the thinning history based on the mountain's emergence up out of the thinning ice sheet. Find out the pattern of ice retreat from the mountain. I've been collecting samples from granite boulders, like this one, for cosmogenic exposure age dating. Many of you are familiar with this method, but for those who aren't, I'm going to dive into the details here for just a moment. This method works as an isotopic clock. The process starts when a boulder is incorporated into the glacier with bedrock plucking or rockfall onto the glacier. The glacier then transports this boulder down valley to its margin. As the ice retreats, the boulder melts out of the ice. Once it's exposed to the atmosphere, it begins getting bombarded by cosmic rays, which are high energy particles that constantly rain down on the Earth. These particles collide with the elements within rock, such as the oxygen within quartz.
There's such a high energy that it causes salvation reaction, which knocks off the neutrons into light isotope. In the case of the oxygen quartz, beryllium-10 is formed. Multiple isotopes form this way. However, beryllium-10 is the best target isotope for the timescales and the rock type that we're looking at. The Katahdin granite has a lot of quartz in it and is perfect for this type of dating. As the boulder sits on the landscape, it accumulates this beryllium at a relatively long, like a sample, and measure the amount of beryllium in the rock to see how long it's been sitting there, and therefore how long it's been since the ice was last in that position and deposited that boulder. These are the sample agents for this area that I processed and farmed. These ages are thousands of years before present. Again, this is a work in progress. There are two main takeaways from these dates. First, the ages at higher elevations are much older than I expected. This could either be the result of a real long-term exposure, which would mean that parts of Katahdin were not covered by ice for the entirety of the last ice age, or, more likely, the summit was covered by minimally erosive coal-based ice that didn't erode enough material to reset the cosmogenic isotope clock. This has been proposed to explain old ages on the summit of Mount Washington in New Hampshire. The youngest age at highest elevation is 18.9 thousand years old, beside the yellow star. This provides a possible date to start with deglaciation on Katahdin. I will examine this further in the future by reflecting more samples. The second main point is that the Basin Pond moraine, drawn in orange, was likely deposited around 16,000 years ago, partway through Heinrich Stadium 1. The combination of the 18.9 thousand year age at higher elevation and the 16,000 year ages of the Basin Ponds moraine, at least 7,000 years lower, suggests a significant ice retreat during the first part of Heinrich Stadium 1. This paused around 16,000 years ago, allowing the formation of the Basin Ponds moraine. After 16,000 years ago, ice continued to retreat down into the lowlands. These are ages from the newly discovered Toad Pond moraine. They indicate that ice was down in the lowlands by about 14,500 years ago. Because the size of glaciers is primarily controlled how much they melt during the summer, this data then supports the idea that summers were warm for part of Heinrich Stadium 1, which again was around 18 to 14.7 thousand years ago. During Heinrich Stadium 1, ice thinned by about a kilometer along the flanks of the top. This massive amount of summertime meltwater reduction may have led to the development of sea ice in the North Atlantic, which caused extraordinary winters. That would be consistent with evidence of rapid ice retreat across the lowlands of Maine 15 to 16,000 years ago. If this is correct, and ice was actually thinning because of warming summers during Heinrich Stadium 1, this would also be consistent with warming in the southern hemisphere, and thus negate the need for a bipolar seesaw during Heinrich Stadium 1. This research is still in progress, and there is a lot more work to do. The goal for this summer is to gather more samples along the flanks of the mountain to develop a more detailed mineralogy. The main target is the Gila-Montana Trail. This trail passes up and over the Basin Ponds moraine, continues up the slope to Molar Peak, following a fairly broad ridge. In this letter, you might be able to see some of these furrows wrapping around the edge of the mountain that cross over the Gila-Montana Trail. These likely represent trim lines of the ice sheet out of thin. Along this trail, we have to be able to collect enough samples to get a better picture of ice thinning during Heinrich Stadium 1. We're also continuing to collect samples on the tablelands to parse out the complicated exposure history, and within the basins to investigate the possibility of alpine glaciers occupying the surface during termination. And with that, thank you, and thank you to the public on these courses, including the Churchill and Sturgis Exchange Project. Thank you.
This is my work on my castle is just in the light of the ring. At the back of the lake, of the Hill Lava, for the last 12,000 years. This project is focused on the long-term drought of the American West that are projected to continue in the same climate. This is due to the shift of precipitation patterns and its outsized impact on the shared water resources, including the snowpack of the Nevada and the Colorado River watershed. Fire activity is also projected to increase in the future, as wildfires are also causing shifts in precipitation patterns and temperatures. My work will be focused on better understanding the mechanisms that drive both drought and fire activity and their links to precipitation patterns. My work will urban hemisphere western. Climate literature suggests that there is a north-south cycle that controls the precipitation patterns across the American West, and this cycle may be connected to the westerly range. Today, the American Northwest has wet conditions, while the American Southwest is undergoing a historic drought. This creates this wet, dry cycle. In the past, this cycle saw some split, with the transition occurring during periods of westerly migration. While this mechanism is still unclear, it is important to understand better the ties between westerly conditions and precipitation patterns to understand the mechanism moving forward in the future to better forecast this drought. My work will focus specifically on all the custody records extracted from the value of the Symposium in the Nevada. Located at 37 degrees north latitude, this Symposium record is influenced by the northern hemisphere western and is currently within the dry part of the modern side. My research questions for this project will be looking at the timing and pattern of western migration during the holidays. So the 12,000-year record will mean an independent proxy for the migration of the western. From this proxy, I will then compare the position of the westerlies' precipitation patterns on a regional and local scale. This will be using independent proxies for hydrologic changes of the Sierra Nevada basin, and it will compare to other data sets collected from the American West. And finally, my research comes down to understanding better the mechanisms that are driving these transitions, precipitation patterns, and larger north-south cycles of slightly dry conditions in the American West. In order to do this, I will focus on many proxies to extract from the 12,000 years the country's sediment record from the Baton Lake. My first proxy is plant wax. Plant wax relies on the biomarkers that preserve and the pharmaceutical. These biomarkers are then preserved within the country record studied down in form. This proxy preserves changes in moisture source, which I will be using as an independent proxy for the position of the westerlies that I will explain on the next slide. This proxy also states changes to the hydrology, measured by both the terrestrial and aquatic plants. And finally, this proxy is also influenced by changes of plant type within the basin. That brings us to my second proxy. A pollen assembly can be assembled to understand changes of the plant community over time, as well as any changes to productivity within this space. By understanding changes to this plant community composition over time, I can correct a plant wax proxy or any influences that plant type has on the record to better extract this shift in the hydrologic changes, so we use to understand better these precipitation patterns. And finally, my third proxy is charcoal. I will be continuously sampling the sediment core to count the number of charcoal pieces within the sediment. With the char analysis program, I will then be able to isolate periods of increased fire activity compared to a background level. And this will give me generally fire activity on a local and regional scale. This fire activity, compared to the hydrologic data, will be able to characterize better how fire activity and recovery is tied to hydrologic shifts. And I will also be able to understand if the plant community composition recovery, along with hydrolysis. These three proxies will give a lot of information on the resilience of the Sierra Nevada and how these patterns. As I mentioned on my last slide, the moisture source data of the plant is used as a independent proxy for the condition of the Western Union. The Nevada lakes are located here, and they are within the central Sierra Nevada. The Sierra Nevada is an ideal place to study the Western Union, as the mountain range itself is thought to steer the direction of the Western Union, either north or south. During periods such as today, when the westerly winds are north of the Baboon Lake, storms track into the southwest, and the moisture source arriving to Baboon Lake have higher hydrogen isotopic values. During periods in which the westerlies are south of the Baboon Lake, storms are tracking into the northwest and are bringing a moisture source that is lower in hydrogen isotopic values. This shift in hydrogen isotopic values is observed within the hydrogen isotopes of the terrestrial plants and alkane, one of the biomarkers that is studied in this plant wax property. This record can be used to independently study the general condition of the Western Union compared to the Baboon Lakes throughout the Holocene. So with that, I have plotted my various data. The three plots on the far left is from the plant wax proxy, and the three plots on the right are stratigraphic analysis. My work for the pollen assemblage and the charcoal analysis are still ongoing, so I do not have any data to share with those today. Starting on the left is my independent proxy for the position of the Western. This is using the hydrogen isotopic values that plant wax biomarker. Data points to the right of this vertical black line indicate the rate in which the westerlies may have been north of the Baboon Lake. Data points to the left of this black line indicate the rate at which the westerlies may have been south of the Baboon Lake. This record shows that there are some changes occurring down core to the relative position of the Western Union. Audit in blue is water availability. Once again, this is a heavy and wax practice. This is using the carbon isotopic values and terrestrial intent. Data points to the right of the black vertical line have higher water availability, and data points to the left have lower water availability. Plotted in red is the relative evapotranspiration rate using the hydrogen isotopic values of aquatic and terrestrial intent. Data points to the right of the line indicate lower relative evapotranspiration rate. Data points to the left are higher evaporation rate. Plotted in green is organic content, and plotted in blue is magnetic susceptibility. And to the far right, I have here my stratigraphic analysis using sediment type and the general field sediment color. I do not currently have interpretations for this record. This is due in part to the calibrations that need to be done, including the pollen assemblage needs to be applied to the water availability proxies to understand if any of these shifts are due to plant type or if they can all be tied directly to hydrological shifts. I'm also working on collecting a modern calibration sample from the Baboon Lake this summer in the Sierra Nevada. This modern calibration will be able to calibrate to understand the current moisture towards to the basin, along with the current isotopic values of plants and their natural biofractionation that heavily influences this record. There will be more data and a lot more interpretations to come as I finish this property record. And with that, I want to especially thank Bob and Sturgis of the Exploration Fund, who made the trip to Cincinnati to run this plant wax data possible. I also want to thank some of my other funding sources, 2016 field crew that extracted from Southern Records, and I also want to thank all the labs in this work possible. Thank you again for listening to my presentation.
I think that brings us to the end of our program for the evening. There's now the poster session. I think the bar is also open.